The oldest city on Earth does not stand in a desert or sleep beneath a mound. It is not waiting under jungle roots, not hidden beneath a temple floor, not preserved behind the sealed door of a forgotten tomb. If it ever existed, if some intelligence before humanity once raised walls, burned fuel, crossed oceans, dug into mountains, and changed the atmosphere around it, then almost all of it is gone. The streets are gone first, the roofs fall, the towers crack, the machines rust, the ports drown, and the rivers move away from their old beds as if the shape of the world has lost interest in memory. Then the harder things vanish. Stone breaks, metal corrodes, glass becomes scattered grit, bones turn to minerals or disappear altogether. A coastline sinks, a plain is buried, a continent drifts, a seabed is folded, lifted, and ground down again. Time does not simply pass over the evidence, time works on it, patiently, chemically, violently, until the surface of a planet becomes less like an archive and more like a crime scene left in the rain for millions of years. This is the strange doorway into the Silurian Hypothesis. It does not begin with a ruined pyramid or a metal object found in coal or a dramatic claim about lost masters of the ancient Earth. It begins with a more unsettling thought. If a technological civilization had existed long before humans, would people even know how to see it? Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. Because the mystery here is not built on secret maps or hidden cities. It is built on erosion, sediment, chemistry, and the uncomfortable fact that Earth is very good at destroying its own past. Across human history, civilization feels old because the scale is human. 5,000 years is an abyss when measured against a single life. 10,000 years reaches back before writing, before kings, before the first monumental cities, into a world of early farming villages, migrating herders, and people who still know the night sky without the glow of electric light. In that span, mountains seem permanent, seas seem ancient, and the ruins of Mesopotamia or Egypt feel like messages from the beginning of time. Yet on a geological scale, all of recorded history is only a brief disturbance at the surface. It is a footprint in damp sand while the tide is already turning. To understand why this matters, imagine looking for modern humanity not 1,000 years from now, but 100 million years from now. The continents have shifted, mountains have risen and worn down, ice sheets have advanced and retreated many times. Most coastlines known today are gone, replaced by other coastlines, other deltas, other shallow seas. Parts of the ocean floor beneath today's shipping lanes have been pulled into the mantle and remade elsewhere. The majority of human building materials have never been designed to survive even a few centuries without maintenance, much less an age long enough to turn forests into coal, reefs into limestone, and mud into shale. A carved stone can last for thousands of years under lucky conditions. A buried foundation can survive long enough for archaeologists to uncover it. But the kind of evidence that makes a civilization feel real to human eyes is fragile because it depends on context. A wall means something because its stones are still arranged as a wall. A city means something because streets, buildings, waste, bones, seeds, and objects remain together in a pattern. Break that pattern, scatter it across deep time, grind it under glaciers, dissolve it in groundwater, or bury it beneath later worlds, and the story becomes almost impossible to read. This is why the question is more disciplined than it first appears. It is not asking whether legends are true. It is asking what kind of signal an industrial species leaves when all ordinary memory has been stripped away. On the surface, the answer seems simple. A civilization would leave buildings, mines, machines, tunnels, roads, satellites, garbage, cemeteries, and scars in the land. But the deeper the clock runs, the less useful those familiar traces become. Earth does not preserve civilization the way a museum preserves artifacts. It preserves unusual chemistry. It preserves abrupt changes in sediment. It preserves mass extinctions, isotope shifts, mineral grains, ash layers, pollen, microfossils, ocean conditions, and sometimes the ghost of a vanished climate. The evidence remains incomplete, and no single kind of clue can carry the whole burden. In this sense, the Silurian hypothesis is almost a mirror turned toward humanity. It asks people to imagine themselves as a future fossil layer, reduced not to monuments or names, but to a thin, strange disturbance in the rocks, a spike in carbon, a pulse of extinction, a change in nitrogen, plastics transformed beyond their original shapes, concrete broken down and mingled with sediment, metals moved from deep ore bodies into unnatural concentrations, artificial radionuclides fading at different rates. Fossilized chicken bones may seem absurd beside the grandeur of human ambition, but the domestic chicken is one of the most numerous land vertebrates shaped by human selection, and its remains may become one of the stranger biological signatures of the modern world. A future geologist might learn less from a palace than from a layer of trash. This is the dry understatement at the heart of the problem. The planet does not preserve what people think is important. It preserves what happens to fall into the right physical conditions. From this angle, the surface of Earth becomes strangely haunted. Every valley is not only a place but a process. Every beach is a temporary arrangement. Every city stands on moving ground. Even when that movement is too slow to feel, there are rocks that still hold the chemistry of vanished oceans. Sudden clay layers that mark catastrophe from the sky, black shales that remember oxygen-starved seas, and coal seams that record buried forests grown before flowers existed. Earth keeps memories, but not human memories. It keeps pressure, temperature, chemistry, and chance. The scientific question exposes a real limitation in how the past is searched. Archaeology reaches into human and near-human time. Paleontology reaches deeper into vanished ecosystems and extinct bodies. Geology reaches deeper still, but with coarser hands. The farther back the search goes, the fewer details remain. Scholars still debate how best to define the human age in geological terms, and even that debate concerns a civilization that is still here, still burning, building, mining, and leaving fresh traces every day. So the opening mystery is not a claim that someone came before. The opening mystery is the silence itself. If humanity is the first technological civilization Earth has produced, the silence makes sense. If there was another, the silence might still make sense. That is what makes the thought experiment so unsettling. Absence is not always simple. Sometimes it means nothing happened. Sometimes it means something happened too long ago, in the wrong place, in the wrong material, under the wrong conditions, and the planet carried on until the evidence became indistinguishable from nature. At the edge of this silence, the familiar world begins to feel temporary. Highways cross continents, ports glitter at night, satellites circle above weather systems, and deep mines cut into rocks older than bones. older than trees, older than complex life in some cases. Yet all of it is happening on a thin, restless skin. Beneath the cities are sediments. Beneath the sediments are older worlds. Beneath those worlds are rocks that have been cooked, crushed, lifted, drowned, and reborn. The question waiting there is not easy. It asks whether civilization is truly a permanent arrival in Earth history, or only another brief pattern written on a surface that has never promised to remember. The name itself sounds like it belongs to an older, stranger Earth, Silurian. It seems to point toward a time before mammals, before dinosaurs, before forests looked familiar, before the land carried the kinds of animals that human eyes would recognize as part of a living world. But the Silurian hypothesis is not really about the Silurian period, and it is not a claim that some known civilization walked the planet more than 400 million years ago. The name is a deliberate borrowing from science fiction, from the imagined Silurians of Doctor Who, intelligent reptilian beings said to have existed before humanity. That origin matters, because it gives the hypothesis a slightly eerie surface while concealing something much more careful underneath. It is not a legend dressed up as science. It is a scientific question wearing the mask of a story. The modern form of the idea is associated with two scientists, Gavin Schmidt and Adam Frank, who approach the problem from climate science, planetary science, and the search for life beyond Earth. Their question is deceptively simple. If an industrial civilization had arisen on Earth millions of years before humans, would it be possible to detect it in the geological record, not whether such a civilization did exist? Not whether hidden ruins are waiting under Antarctica or buried beneath basalt in some forbidden place. The question is narrower, colder, and more interesting. What would count as evidence after deep time had finished with the obvious things? That shift changes everything. Popular imagination usually begins with artifacts. It expects a strange metal object, a buried machine, a wall that should not be there, a map with impossible coastlines, a crystal skull, a doorway under the ocean, some object that seems to violate the ordinary sequence of history. But science does not begin by needing the past to be spectacular. It begins by asking what processes preserve and what processes erase. It asks whether a proposed signal would survive, whether it could be distinguished from natural causes, and whether alternative explanations are more likely. The evidence remains incomplete by nature, and the deeper the timescale becomes, the more discipline the question requires. The reason the Silurian hypothesis feels powerful is not because it opens the door to easy claims. It is powerful because it closes many of them. If a civilization is only thousands of years older than Mesopotamia, Egypt, the Indus cities, or the first known urban worlds, archaeology would expect to find something: pottery, bones, hearths, tools, settlements, waste, plant remains, quarry marks, altered landscapes, burial places, or a break in the pattern of known cultures would eventually appear somewhere, even if the record were damaged. Human civilization may feel ancient, but its material traces are abundant precisely because it is recent. The farther back one pushes an alleged civilization, however, the less archaeology can do, and the more the problem belongs to geology. This is where the idea becomes unsettling in a different way. A civilization 10,000 years older than known history would be a radical archaeological claim. A civilization 10 million years older would be a geological problem. A civilization 100 million years older would be almost entirely a chemical and stratigraphic problem. The kind of proof people usually imagine would probably be the first proof to vanish. A monument may survive a desert for several thousand years, but it is unlikely to survive a continent's long reshaping unless it is buried in exactly the right conditions and later exposed in exactly the right way. A metal machine may seem durable, but corrosion, pressure, groundwater, heat, and deformation turn durability into a relative term. Even fossils are not common compared with the number of living things that have existed. Most organisms die and leave nothing. Most environments do not become archives. The Silurian hypothesis therefore turns attention away from ruins and toward planetary disturbance. A technological species does not only make objects, it changes flows of energy and matter. It extracts carbon that was buried for millions of years and releases it into the atmosphere. It mines metals and redistributes them. It alters rivers, forests, coastlines, soils, and animal populations. It creates synthetic chemicals that nature did not previously make in that form. It produces waste that spreads far beyond the cities that made it. If it becomes global, it leaves a global signal, and a global signal has a better chance of entering the rock record than a single temple, even a magnificent one. Yet even there, the problem does not become easy. Earth has already produced events that look, in broad outline, like planetary disturbance. Massive volcanic eruptions have poured greenhouse gases into the atmosphere. Asteroid impacts have thrown dust and chemistry around the globe. Ocean anoxic events have changed the chemistry of seas and left dark organic-rich sediments. Sudden warming events have shifted carbon isotopes. Mass extinctions have removed large parts of life's diversity. None of these require civilization. They belong to Earth's own unruly machinery. So if a future geologist finds a strange carbon spike, an extinction pulse, or unusual sediment chemistry in the distant past, the first explanations must remain natural unless the evidence points clearly elsewhere. That is what separates a useful hypothesis from a fantasy. It does not assume its conclusion. It asks how the conclusion would be tested and how it could be wrong. A hidden industrial species should not be invoked to explain every ancient mystery. Because Earth already contains enough volcanoes, impacts, climate shifts, oxygen crises, sea level changes, biological revolutions, and tectonic upheavals to explain many dramatic scars in the rocks. Scholars still debate the details of some ancient environmental crises, but debate is not an empty space waiting to be filled by lost empires. Uncertainty is not permission to invent. It is a boundary that careful storytelling has to respect. Still, the thought experiment refuses to disappear because it touches a deeper scientific anxiety. Humanity is now leaving marks that may last far longer than human institutions, languages, or nations. If another intelligence from the far future tried to reconstruct the present age, it might not find the internet, the flags, the names of cities, or the stories people believed about themselves. It might find an abrupt reshuffling of carbon. It might find a layer enriched with combustion residues and industrial metals. It might find fossil traces of species moved across continents, extinctions clustered together, and deposits shaped by materials that were manufactured in enormous quantity. The world that feels intensely historical from within may become almost anonymous from outside. That anonymity is part of the dread. Civilization imagines itself through memory. Geology recognizes it through residue. The great libraries, the data centers, the monuments, the towers, the harbors, the machines in orbit, the scars of mining, the bones of domesticated animals, and the altered chemistry of the atmosphere all have different survival chances. Many of the things that define a civilization to itself are poor candidates for a deep time preservation. Many of the things a civilization barely notices, the smoke, the waste, the sediment, the altered ratios of elements, may become its most enduring signature. So the question from science fiction becomes a question about method. Could Earth have hosted an earlier industrial civilization and erased nearly everything familiar about it? In principle, deep time makes erasure frighteningly plausible. In practice, no convincing evidence has been found. The silence remains the mainstream answer, but it is no longer a simple silence. It is a silence filtered through erosion, burial, metamorphism, ocean recycling, and the selectivity of preservation. The Silurian Hypothesis asks people to stand inside that silence without rushing to fill it. It asks them to see the planet not as a stage built for human history, but as an ancient system where even intelligence may be temporary unless it leaves the right kind of scar. Civilization is a word that becomes less stable the farther it is carried away from human time. In ordinary history, it points towards cities, agriculture, writing, organized labor, law, trade, temples, roads, irrigation, rulers, specialists, storage, war, and memory. It points toward people living in settlements large enough that no single family can hold the whole pattern in view. It points toward grain counted in storerooms, clay tablets pressed with signs, canals cut through floodplains, ships carrying goods between coasts, and strangers meeting under rules that did not exist in small bands of hunters and gatherers. By that measure, civilization is recent, almost shockingly recent. The first great urban societies rise only a few thousand years before the present, in the river-fed landscapes of Mesopotamia, Egypt, the Indus Valley, China, the Andes, and Mesoamerica. They appear after a long human prelude of stone tools, fire, language, art, migration, extinction, adaptation, and survival. They're old enough to feel mythical, but young enough that many of their bricks, bones, and broken pots still lie within reach of a trowel. Geology uses a colder definition. It has no natural category for kings, markets, priesthoods, or written archives. It does not care whether a society has poetry or bureaucracy. It asks whether the activities of a species become large enough to disturb the planet in a way that can be preserved. A village may transform a hillside, but a planet may forget it. A city may change a river, but later floods can erase the pattern. A civilization that never industrializes may leave wonderful archaeological traces and almost no global geological signature. In deep time, the question is not simply whether beings are clever, social, artistic, or urban. The question is whether they move enough matter, burn enough stored energy, transform enough ecosystems, and alter enough chemistry to leave a mark that can survive when the buildings are gone. This difference is essential because the Silurian hypothesis is not really looking for civilization in the historical sense. It is looking for something closer to industrial planetary impact. A Bronze Age city, no matter how sophisticated, does not resemble a coal-burning, oil drilling, plastic making, nuclear testing, nitrogen fixing, global shipping civilization. Ancient Mesopotamia can change canals, soils, forests, and human destiny. But it does not rewrite atmospheric chemistry on the scale of modern industry. The early city is enormous in human memory and small in planetary metabolism. The modern industrial world is the opposite. It may be morally confused, politically temporary, and young enough to be absurd. but it moves carbon that was buried before humans existed, extracts metals from deep rock, manufactures minerals and compounds unknown to previous ecosystems, and spreads its residues from mountain snow to ocean trenches. The distinction creates a strange hierarchy of visibility. The societies that matter most to historians may not be the societies most visible to future geologists. A literate kingdom that endures for 1,000 years may leave inscriptions, temples, cemeteries, and stories. But if those remains are not preserved, buried, and later found, they disappear as a recognizable world. An industrial society that lasts only a few centuries may leave a thinner cultural story but a sharper chemical scar. In the deep time record, duration matters, but scale matters too. A brief, intense disturbance can be easier to detect than a longer, gentler pattern. This is why a single asteroid impact can become a boundary recognized around the planet, while countless rich ecosystems leave only patchy and local clues. Humanity's own story shows how sharply these scales can differ. For most of the existence of Homo sapiens, people leave traces that are extraordinary to archaeologists and nearly invisible to geology. Stone tools scatter across landscapes, hearths darken cave floors, red ochre marks bodies and objects, shell beads, carved bone, pigments, burials, footprints, campsites, and kill sites reveal minds alert to social meaning and environment. Yet these are not global industrial signals. They are fragile constellations of evidence, preserved unevenly, often by luck. A cave in the right climate becomes a chamber of memory. An open plain may keep almost nothing. A coastal settlement may drown beneath a rising sea and become nearly impossible to recover. What survives in the record suggests great complexity long before cities, but not an earlier industrial layer. The agricultural revolution changes the pattern, but still not in a simple way. Farming societies clear forests, move species, shape soils, domesticate plants and animals, settle more densely, and produce landscapes that can outlast the people who made them. Terraces climb hillsides, irrigation alters floodplains, grazing changes vegetation, rice paddies, wheat fields, orchards, and pasture lands become living technologies. Over thousands of years, these changes matter deeply. Some scholars still debate how early human land use began to influence climate, especially through deforestation, methane from rice agriculture, and the expansion of livestock. But even if early agriculture left a measurable environmental influence, it is not the same as the sudden combustion of fossil carbon that marks the industrial age. The tempo changes, the energy source changes, the signature changes. A geological civilization, then, is not necessarily the same as a cultural civilization. It is a species or system of life that becomes a geophysical force. It pulls ancient carbon from rocks and sends it into air and sea. It alters the nitrogen cycle by fixing atmospheric nitrogen into fertilizers on a scale beyond natural lightning and microbes alone. It concentrates rare elements. It creates combustion byproducts and distributes them widely. It causes extinctions not merely by hunting one species in one region, but by transforming habitats across continents. It changes erosion through roads, farms, dams, mines, and deforestation. It may create what future scientists would read not as a city plan, but as an interruption in the normal rhythm of sediments. The lesser-known strangeness is that a civilization may become more legible after its identity has vanished. A future layer may reveal that something burned fossil carbon, but not what language it spoke. It may show that nitrogen cycles changed, but not what political arguments filled the cities. It may preserve the bones of domesticated animals in staggering numbers, but not the names people gave them. It may reveal synthetic molecules or their degraded descendants, but not the faces of the chemists. It may preserve traces of concrete-like materials, aluminum concentrations, altered river deposits, and soot, while every museum label, treaty, song, and family photograph is gone. The planet may remember the metabolism and forget the mind. That idea places known human civilization in a humbling frame. The ancient cities that mark the beginning of written history arise during the Holocene, a warm interval following the last ice age, when climates stabilize enough in many regions for farming, herding, storage, and urban life to intensify. Before that, for hundreds of thousands of years, humans and their relatives live in worlds that shift under ice, drought, flood, and migration. Before humans, mammals diversify after the dinosaurs. Before mammals dominate, reptiles, amphibians, fish, invertebrates, forests, reefs, and microbial worlds pass through their own revolutions. Earth is not a human story with a long prologue. It is a planetary story in which humans appear very late, and cities arrive almost at the end of the final page. So when the question asks whether humans were the first civilization on Earth, the careful answer depends on what kind of civilization is being discussed. Humans are the first known builders of cities, writing systems, states, global industry, and planet-scale technology. No reliable evidence shows another industrial species before us, but the Silurian hypothesis presses against the word known. It reminds us that deep time is not an empty museum waiting to display all that once happened. It is selective, destructive, and uneven. A civilization can be obvious to itself and nearly invisible to the future. The mystery does not grow by inventing lost empires. It grows by realizing how thin the bridge is between existence and evidence. The human footprint feels enormous because people live inside it. Cities glow from orbit. Roads cut across deserts and forests. Ports reshape coastlines. Mines open wounds in mountains. Dams hold back rivers that once carried silt freely toward the sea. Airports, railways, power stations, farms, suburbs, reservoirs, canals, factories, satellites, cables, and waste grounds form a second geography laid over the first. From within the present, it seems impossible that such a world could ever disappear. It feels too large, too hard, too deeply rooted in the land. Yet the size of a civilization is not the same as its durability. Much of the modern world survives only because it is maintained every day by people, machines, electricity, drainage systems, repair crews, supply chains, and constant replacement. Remove that maintenance, and the built world begins to lose its confidence almost immediately. A city without people does not become an instant ruin in a dramatic flash. It fails in quiet stages. Water enters first. Rain finds cracks in roofs, joints in walls, seams in pavement, and tunnels under streets. Pipes burst when they freeze or corrode. Storm drains clog with leaves, soil, trash, and roots. Basements flood. Concrete absorbs moisture. Steel reinforcement begins to rust, and as it rusts it expands, breaking the concrete that once protected it. Windows shatter under weather, falling branches, heat stress, or small impacts. Once a building is open to the air, the interior becomes part of the outside world. dust settles, seeds arrive, birds nest, insects feed, mold spreads through the damp, floors sag. The difference between architecture and habitat begins to blur. Modern buildings often look permanent because they are massive, but many are composites of materials that age badly when neglected. Concrete can endure under some conditions, but reinforced concrete carries its own weakness inside it. Steel and concrete work together when new, yet time, salt, water, and carbonation slowly attack that partnership. Skyscrapers depend on pumps, elevators, sealed envelopes, fire protection systems, and controlled drainage. Underground transit systems depend on constant removal of water. Coastal cities depend on barriers, pumps, maintained foundations, and the assumption that sea level, storm patterns, and river flow will remain manageable. When those systems stop, gravity and water take over with no sense of historical importance. Roads also begin to vanish more quickly than their scale suggests. Asphalt softens, cracks, oxidizes, and breaks under heat, cold, and plant roots. In wet climates, small cracks become channels for water, and water carries in the soil. Grass appears in seams, then shrubs, then trees. Their roots pry open the surface. Their leaves form soil. Animals burrow. Frost breaks the pavement further where freeze-thaw cycles occur. In deserts, wind buries roads under sand or strips them into fragments. In mountains, landslides erase them. On coasts, storms tear them apart. A highway may remain visible for a long time in the right landscape, but it is not eternal. It is a surface condition, and surfaces are where Earth is least willing to hold still. Metal seems more promising, but even metal is not a simple archive. Iron rusts, copper corrodes, aluminum forms protective oxides but can still degrade, especially in harsh environments. Ships sink and become artificial reefs before they collapse into corrosion products and scattered pieces. Cars lose paint, rubber, fabric, wiring, fluids, and structural strength. Machines are not only metal, they are also plastics, seals, coatings, electronics, lubricants, and countless small parts that do not age together. A recognizable machine depends on the arrangement of its parts. Deep time does not need to erase every atom. It only needs to destroy the arrangement. Once pattern is lost, technology becomes a geochemical curiosity, not an object that announces what it was. Plastics complicate the picture because they're both fragile and persistent. A plastic bottle exposed to sunlight becomes brittle and breaks into smaller pieces, but those pieces may linger as microplastics in soils, rivers, lakes, and marine sediments. Some polymers may survive in altered form far longer than the object's original shape. Others may be degraded by heat, pressure, oxidation, microbes, or chemical processes. Scholars still debate how future rocks will preserve the many varieties of synthetic material produced today, because the industrial age is very young, and the full fate of these materials across geological time remains uncertain. The familiar shape of a bag, bottle, net, tire, or film wrapper is unlikely to endure for millions of years in a readable way. But the chemical and sedimentary consequences of mass plastic production may leave a broader and stranger trace. Bones are another misleading symbol of permanence. Museums make skeletons seem inevitable, but fossilization is rare. Most bones are destroyed by scavengers, weathering, acidity, microbes, trampling, water movement, or simple exposure. A skeleton becomes part of the long record only when it's buried quickly enough and chemically altered under suitable conditions. Even then, it may later be crushed, dissolved, metamorphosed, or eroded before any future observer can find it. Human bones. Despite the billions of people alive today and the billions who've lived before, are not guaranteed to become a clean global fossil layer. Cemeteries may be disturbed by erosion, groundwater, construction, sea level rise, soil chemistry, and later geological change, cremation, scattering, decomposition, and varied burial practices further complicate the signal. One surprising candidate for future fossil fame is not the human skeleton, but the remains of animals humans have multiplied. The domestic chicken, raised in extraordinary numbers, carries a body shaped by selective breeding and industrial farming. Its bones are deposited in landfills, farms, processing sites, and waste streams across the world. To a future paleontologist, a sudden abundance of oddly shaped chicken remains may say something sharp about the age of humans, perhaps more sharply than many heroic monuments. Cattle, pigs, sheep, dogs, cats, rats, and commensal species moved by people also form part of this altered biological signature. What survives in the record suggests that civilization may be remembered less by its leaders than by its livestock, pests, and refuse. Monuments have better odds when built from durable stone and buried under protective conditions, but even monuments are not immune. Limestone dissolves in acidic water, sandstone erodes grain by grain, granite lasts longer but still fractures, weathers, and can be broken by tectonic movement. A statue loses its face long before it loses its mass. An inscription needs surface detail, and surface detail is precisely what weather destroys. A pyramid, temple, or megalith may persist for astonishing spans by human standards. Yet geological time is not satisfied with astonishing. Millions of years introduce mountain building, burial, uplift, rivers, glaciation, salt, heat, and pressure. A monument can become rubble, then sediment, then rock, then metamorphic texture. Its cultural meaning gone long before its minerals disappear. The fragility of the human footprint is not a comfort, and it is not an argument that nothing remains. Humanity is leaving traces on an immense scale. Landfills may become unusual deposits. Mines may become strange voids or mineralized scars. Cities may form layers of brick, glass, concrete, ceramics, metals, and altered soils. Nuclear tests leave radionuclide signatures. Fossil fuel combustion spreads soot and fly ash. Agriculture changes pollen records and erosion patterns. Yet the recognizable world of human intention is much more vulnerable than the planetary consequences of human activity. The skyline disappears before the sedimentary anomaly. The names vanish before the chemistry. The story dissolves before the scar. This is why the Silurian question keeps returning to humility. If modern civilization ended and enough time passed, future investigators might not find a frozen city waiting like a perfect museum. They might find fragments, residues, odd layers, disturbed cycles, biological rearrangements, and chemical hints. They might argue over whether those hints represent industry, disaster, volcanism, climate instability, or some combination no single explanation fully accounts for. The human age feels solid while people stand inside it. But seen from deep time, it is a brief construction on a restless surface, held together by maintenance, luck, and the illusion that the present is harder to erase than everything that came before. What geology preserves is rarely what a civilization would choose to save. It does not preserve importance. It preserves conditions. A love letter, a law code, a treaty, a census, a map, a prayer, a machine blueprint, a child's toy, a crown, a passport, a painting, and a hard drive may contain entire worlds of meaning. But to the Earth they are only materials exposed to oxygen, water, pressure, microbes, heat, burial, abrasion, and chance. A sheet of paper disappears. A digital archive depends on a delicate chain of electricity, hardware, formats, and maintenance. A carved inscription lasts longer, but only if its surface survives. Geology is not interested in intention. It keeps what enters sediment, what becomes chemically unusual, what gets buried fast enough, what avoids being cooked too thoroughly, and what later returns to the surface in a form someone can still recognize. This is one of the hardest shifts in perspective. Human beings look for the past through objects: a pot, a wall, a blade, a skeleton, a bead, a foundation, a hearth, a footprint. Archaeology is powerful because human time is close enough that objects can still hold shape. Even when broken, they often remain arranged in patterns of use. A scatter of flint flakes can reveal tool-making. A patch of burned earth can reveal a fire. A row of post holes can suggest a house whose wood has vanished. A layer of fish bones can suggest diet, trade, season, or ritual. Archaeology works with fragments, but those fragments still belong to a recognizable world. Deep geology works differently. It often deals with traces whose makers are gone beyond identification. It reads mud that became shale, sand that became sandstone, coral reefs turned limestone, volcanic ash transformed into mineral layers, ancient soils hardened into paleosols, and ocean sediments that settled grain by grain in darkness. It records a floodplain, not the name of a farmer. It records an extinction, not the fear of the creatures living through it. It records a chemical shift, not the cause with a label attached. In deep time, the past becomes less like a library and more like a weathered ledger, where only the biggest transactions remain. The basic unit of memory is often sediment. Rivers carry eroded rock, soil, organic matter, pollen, bones, shells, and chemical residues toward low places. Lakes collect seasonal layers. Deltas build outward into seas. Floods bury surfaces quickly. Ocean floors receive a slow rain of plankton shells, dust, ash, and minerals. Swamps trap plant material that may become coal under pressure and time. Deserts preserve dunes, footprints, burrows, and rare remains when conditions are right. Volcanic ash can seal a landscape in a moment, preserving details that ordinary erosion would destroy. But most surfaces are not sealed in this way. Most are exposed, reworked, eaten, scattered, washed, oxidized, or simply erased before they ever become part of the long record. This selectivity explains why fossils are both precious and misleading. Life has filled Earth for billions of years, yet the fossil record is only a tiny and uneven sample of that life. Hard parts preserve better than soft bodies. Marine environments often preserve better than uplands. Creatures living near sediment-rich water have better odds than animals dying on dry open ground. A shell on a seafloor has a better chance than a bird in a forest canopy. Even then, preservation is only the first gamble. The fossil must survive burial, mineral change, tectonic deformation, erosion, and discovery. A species may thrive for hundreds of thousands of years and leave only a few bones, or none at all. The evidence remains incomplete, not because the past was empty, but because preservation is rare. For a civilization, the same rule becomes even more severe. A city stands in an environment chosen for living, trading, farming, defense, water access, or transportation, not necessarily for long-term geological preservation. Many cities are built on riverbanks, coastlines, deltas, and fertile plains, exactly the places where erosion, flooding, subsidence, sediment shifting, and sea level change can be intense. These places can preserve remains beautifully over thousands of years, but over millions they may be buried deeply, compacted, drowned, uplifted, eroded, or transformed. Coastal evidence is especially vulnerable because sea levels rise and fall repeatedly. A harbour that seems central to a civilization can vanish beneath marine sediment, be ground by waves, or be stranded far inland by tectonic uplift. Geology is much better at preserving large environmental signals than preserving deliberate design. A mass extinction can appear as a sudden disappearance of many fossil forms across layers. A major volcanic episode can leave lava flows, ash beds, mercury anomalies, and carbon cycle disruption. An asteroid impact can leave shocked minerals, tiny glassy spherules, unusual elemental concentrations, and a boundary layer spread across distant regions. An oxygen-starved ocean can leave dark shales rich in organic matter. A warming event can leave a carbon isotope excursion, changes in fossil communities, clay mineral shifts, and signs of altered rainfall or erosion. These traces are not personal, but they are durable because they are distributed widely and tied to physical systems. This is why the strongest possible trace of a vanished industrial civilization would probably not be a machine. It would be a pattern, a sudden disturbance in carbon isotopes, suggesting rapid transfer of buried carbon into the atmosphere and ocean. A shift in nitrogen linked to artificial fixation or fertilizer use. Unusual concentrations of metals from mining and industry, synthetic organic compounds, or their breakdown products, appearing in sediments where they have no natural reason to appear, a global layer of combustion particles from widespread burning, a sharp biological turnover with extinctions, invasive species, domesticated species, and ecosystem simplification. The signal would need to be broad, unusual, and difficult to explain through known natural processes. Even then, scholars would argue over interpretation, because no single explanation fully accounts for every deep-time anomaly without careful testing. A lesser-known complication is that the rock record is full of gaps. These gaps are called unconformities, and they can represent enormous spans of missing time. A surface may be eroded for millions of years before new sediment covers it. Layers that once existed may be removed entirely. In some places, the boundary between two rocks looks simple, but the time missing between them could be longer than the entire history of human civilization by thousands of times. If an ancient industrial episode happened during an interval later erased by erosion, or in rocks later melted, metamorphosed, or subducted, its evidence could be gone in the most literal sense. Not hidden, gone. Ocean crust adds another problem. The seafloor is young compared with the continents because plate tectonics constantly creates new ocean crust at ridges and destroys old crust at subduction zones. Much of the ocean floor older than about 200 million years has been recycled into the mantle. If a hypothetical civilization lived mostly on coasts or islands in an ancient ocean basin, vast portions of its physical setting might no longer exist. Continental rocks can be much older. But they too are changed by erosion, burial, mountain building, faulting, heating, and chemical alteration. Earth is not a static storage room. It is a machine that makes, breaks, buries, and remakes its own surface. Yet the planet is not without memory. Some rocks preserve astonishingly delicate clues. Ancient raindrop impressions can survive in hardened sediment. Ripple marks from vanished shores can remain for hundreds of millions of years. Fossil burrows can reveal behavior even when the animal itself is gone. Pollen grains can reconstruct ancient vegetation. Tiny shells can record ocean temperature and chemistry. Ice cores can trap bubbles of old atmosphere. Though only across relatively recent geological spans, tree rings, lake varves, cave deposits, and coral skeletons can hold seasonal or annual records, but these are fragile compared with the abyss of deep time. The farther back the search goes, the more the record becomes patchy, compressed, and indirect. So the strange truth is that geology may be able to detect a civilization while failing completely to describe it. It might see that something happened, that carbon moved too quickly, that certain elements appeared in unusual abundance, that ecosystems collapsed or reorganized, that sediments carried strange residues, that erosion patterns changed, that fire became widespread, that the atmosphere and oceans shifted together, but it might not reveal faces, voices, languages, beliefs, or machines. It might not even prove intelligence unless the pattern were unmistakably artificial. The civilization would not return as itself. It would return as a disturbance. This is the silence beneath the stones. The Earth can remember a temperature change better than a constitution. It can preserve a chemical scar longer than a palace. It can hold the ghost of an ocean more faithfully than the story of those who sailed it. For the Silurian hypothesis, this does not make a lost civilization likely. It makes the search more austere. It strips away the romance of perfect ruins and replaces it with sediment, isotopes, erosion, and uncertainty. If something before humanity ever rose high enough to alter the planet, the proof would not necessarily look like civilization at all. It might look, at first glance, like one more strange layer in the long and restless memory of Earth. The Anthropocene begins as a disagreement before it becomes a layer. To many people, the word already feels obvious. Humanity has altered the atmosphere, warmed the climate, acidified the oceans, moved species between continents, cut forests, dammed rivers, mined mountains, spread plastics, reshaped the nitrogen cycle, and pushed many forms of life toward extinction. Yet in formal geology, naming an age is not simply a matter of importance. It requires a boundary that can be identified in sediments and rocks, a signal sharp enough and widespread enough to serve as a marker for future observers. Scholars still debate how best to define the human age, and the official geological timescale has not simply accepted every popular use of the term. That tension is useful, because it shows exactly how strict Earth history can be. Even humanity, with all its noise and fire, must pass through the narrow gate of preservation. For the Silurian hypothesis, the Anthropocene becomes the test case. If modern civilization vanished, what would remain when the cities were gone? Not in a century, when towers might still stand as haunted shells. Not in 10,000 years, when some monuments, landfills, mines, tunnels, and ruins might still be recognizable. The more difficult question lies much farther out, when archaeology has faded into geology. If a future intelligence, human or otherwise, were reading Earth after millions of years, What would it see? The answer is unlikely to be a map of nations or a list of empires. It would be a disturbance, brief and intense, written into air, water, sediment, bones, and chemistry. The first and most obvious signal is carbon. Industrial civilization draws heavily on fossil fuels, which are ancient stores of organic carbon buried in coal, oil, and natural gas. When burned, that carbon moves rapidly into the atmosphere and oceans. In geological terms, the speed matters as much as the amount. Earth has seen large carbon releases before, but the modern pulse is abrupt on the scale of sedimentary records. Future geologists might not find smokestacks, engines, or power plants, but they could detect a shift in the ratio of carbon isotopes. Fossil carbon carries a different isotopic signature than carbon cycling through the recent biosphere, and burning enough of it changes the balance. The planet may forget the shape of a refinery while remembering the breath of one. Carbon does not travel alone. The industrial age also changes nitrogen. Modern agriculture depends heavily on artificial nitrogen fixation, turning atmospheric nitrogen into fertilizer at enormous scale. That fertilizer feeds crops, but it also runs into rivers, lakes, and oceans, where it can drive algal blooms and oxygen-starved waters. A future sediment layer might preserve changes in nitrogen isotopes, organic-rich deposits, or signs of altered productivity in coastal zones. Phosphorus moves too, mined from rocks and spread across fields, then washed into waterways. These cycles were already part of Earth before humans, but modern civilization accelerates and reroutes them in unusual ways. What survives in the record suggests not merely a clever animal, but a species that began interfering with planetary metabolism. Combustion leaves another signature. Burning coal and oil does not only release invisible gases, it spreads soot, fly ash, and tiny industrial particles over wide areas. Some of these particles are remarkably distinctive under a microscope, especially the spheroidal carbonaceous particles associated with high-temperature fossil fuel combustion. They can settle into lakes, peatlands, soils, and marine sediments. They are not monuments, but they may be more durable as markers than many monuments. A palace can be quarried, shattered, or eroded into anonymity. A global rain of combustion particles can become a thin, dark whisper across many sedimentary archives. The evidence remains incomplete, and preservation will vary from place to place. But the pattern is exactly the kind of thing geology is trained to notice. Then there are the materials that nature did not make in such forms before the human industrial age. Plastics spread through rivers, beaches, soils, deep ocean sediments, and living bodies. Some break down into fragments too small to see without instruments. Others become mixed with sand, tar, shell, glass, and stone-like aggregates along shorelines. Over deep time, many plastics may degrade or transform, and scholars still debate their long-term geological fate. Yet the scale of production is so large that future rocks may preserve either the materials themselves, altered chemical residues, or unusual sediment textures associated with synthetic debris. The future may not find a perfect plastic bottle with a label still attached. It may find a horizon where the sedimentary world briefly contains the degraded shadow of manufacturing. Metals add to the disturbance. Industrial society mines, refines, concentrates, and redistributes elements at scales far beyond ordinary biological activity. Lead, copper, zinc, chromium, nickel, aluminum, rare earth elements, and many other materials move from ore bodies into cities, machines, electronics, pigments, pipes, batteries, and waste streams. Some are dispersed through air and water, others accumulate in landfills, harbour mud, urban soils, and industrial deposits. Future geologists might detect abnormal concentrations or combinations of elements, but interpretation would not always be simple. Volcanic activity, hydrothermal systems, erosion of ore deposits, and natural geochemical anomalies can also concentrate metals. No single explanation fully accounts for every strange enrichment without context. The power of the Anthropocene signal lies in the combination of clues, not in one isolated marker. The nuclear age creates one of the sharpest timestamps. Above-ground nuclear testing scattered artificial radionuclides across the globe, including isotopes that did not occur naturally in the environment in the same pattern. Some decay quickly, others last longer. Their presence can mark the mid-20th century with unusual precision in recent sediments. Ice, corals, tree rings, and soils. Over millions of years, many radioactive signals would fade, depending on half-life, burial conditions, and detection limits. But while they last, they form a striking example of how a short technological episode can create a worldwide marker. The irony is hard to miss. A civilization may leave one of its cleanest geological timestamps not through its art or wisdom, but through the fallout of its most dangerous weapons. Biology may record the human age even more dramatically. The modern world is marked by extinction, habitat fragmentation, overhunting, pollution, climate change, invasive species, and the massive expansion of domesticated animals. Future fossil layers may show a sudden decline in many wild species, an increase in animals associated with humans, and a strange homogenization of life across continents. Rats, mice, cats, dogs, pigs, cattle, and chickens follow human systems into places they would not have reached alone. Crops and weeds spread beyond their original ranges. Marine organisms travel in ballast water and on ship hulls. The biological map of the planet becomes scrambled. In deep time, this may look like a planetary mixing event tied to an extinction pulse. One lesser-known possibility is that the most abundant future fossils of the human age may not be human at all. They may be the bones of broiler chickens, animals bred into forms dramatically different from their wild ancestors, and produced in numbers so vast that they become part of the sedimentary signature of civilization. Landfills, farms, slaughter sites, and waste deposits could preserve them in unusual density. If the bones fossilize, they would point to a world where one species reshaped another species' body for food on a planetary scale. That is a strange legacy. But geology is full of strange legacies. It does not care whether a trace feels dignified. It cares whether it survives. The Anthropocene also changes erosion and sedimentation. Deforestation exposes soils. Farming moves earth. Roads and construction alter runoff. Dams trap sediment that would have reached deltas and coasts. Mining produces tailings and artificial landforms. Cities create layers of rubble, concrete, brick, glass, ceramics, asphalt, and compacted waste. Coastal engineering changes shorelines. River systems are straightened, blocked, deepened, or forced into channels. These changes may be local, regional, or global, and many will be destroyed or reworked. But together they show civilization acting like a geological agent. Not merely living on the planet, but changing the way the planet moves its own materials. This is why the Anthropocene is so valuable to the Silurian question. It gives scientists a living example of an industrial species becoming visible to geology. It shows which traces are likely to be sharp, which are likely to fade, and which may be confused with natural events. It also reveals the humility of the search. Even with modern humanity all around, defining its exact geological boundary is difficult. The signal is real, but its official meaning is debated. The layer exists in many forms, but its preservation will be uneven. If identifying the human age is complex while humans are still here, then identifying a hypothetical civilization tens of millions of years old would be far harder. The test case leads back to the same unsettling lesson. Future Earth may remember humanity as carbon, nitrogen, ash, plastic residue, metal enrichment, extinction, chicken bones, radionuclides, altered sediments, and a brief climate disturbance. It may not remember names. It may not remember cities. It may not remember the difference between a temple and a shopping mall. If humans want to know how an earlier civilization might appear after deep time, they must first accept how their own world may appear not as a grand monument at the center of history, but as a thin, complex, damaged, chemically unusual layer in the long archive of the planet. If a civilization is erased as architecture, it may survive as a signal. That is the narrow path the Silurian Hypothesis follows beneath the familiar surface of history. It does not expect a future observer to find a palace from 100 million years ago, with doors still aligned and inscriptions waiting to be translated. It expects something far less romantic and possibly far more durable, a layer where the ordinary behavior of the planet changes too quickly, too widely, and in too many connected ways to ignore. The signal would not need to say who built the civilization. It would first need to say that the Earth system was disturbed in a pattern that resembles industry, rather than ordinary climate variation alone. Carbon remains the first clue because carbon is one of Earth's great storytellers. It moves through air, ocean, rock, soil, plants, animals, and buried fossil stores. When ancient organic carbon is released rapidly, the atmosphere and oceans carry the signature. In rocks, this may appear as a carbon isotope excursion, a shift in the balance between heavier and lighter forms of carbon. Such shifts are not automatically artificial. They can be caused by volcanic outgassing, methane release, changes in organic burial, ocean circulation, wildfires, weathering, or other natural disruptions. But an industrial civilization based on fossil fuel combustion would also create a carbon signal, and if that signal came with warming, ocean acidification, biological stress, and unusual pollutants, the pattern would become more interesting. One mark alone would be ambiguous. A cluster of marks might begin to speak. The challenge is that Earth has spoken in similar tones before. The rock record contains episodes of rapid warming, ocean stress, extinction, and carbon cycle disruption without any need for technology. This is why the Silurian Hypothesis cannot simply point to an ancient carbon spike and declare civilization. It has to ask whether the whole suite of evidence fits. Was there a rapid injection of carbon? Did temperatures rise? Did oceans lose oxygen? Did species disappear in a pattern suggesting ecological collapse? Did sediments show sudden erosion from disturbed landscapes? Did unusual chemical compounds appear? Were metals redistributed in ways that seemed difficult to explain by volcanism or ordinary weathering? The evidence remains incomplete, and the deeper the layer, the more every answer arrives with damage already done to it. Nitrogen and phosphorus could add further texture. A technological species with intensive agriculture might alter nutrient cycles on a scale visible in lakes, deltas, and shallow seas. Fertilizer runoff can drive blooms of algae and other organisms, leading to oxygen-poor bottom waters when that organic matter decays. In the geological record, this might become dark, organic-rich sediment, chemical signs of low oxygen, or shifts in nitrogen isotopes. Yet nature can also create nutrient surges. Weathering, volcanic ash, ocean circulation changes, sea level shifts, and climate-driven runoff can all feed biological productivity. Again, the clue is not the existence of one change. It is the combination, timing, speed, and global spread of many changes together. Synthetic compounds would be more striking, at least in principle. A species capable of advanced chemistry may manufacture substances that natural processes rarely or never produce in the same way. Plastics, persistent organic pollutants, industrial solvents, pesticides, flame retardants, and many other compounds can move through air, water, soil, and living bodies. Some may break down quickly. Others persist long enough to enter sediments over millions of years. Many original molecules may not survive intact, especially under heat, pressure, oxidation, and microbial activity. But their breakdown products, unusual carbon structures, or associated chemical anomalies might remain. Scholars still debate how recognizable such residues would be after deep time, because modern synthetic chemistry has existed for only a geological instant. The future of these traces is itself an experiment already underway. Combustion residues may offer a cleaner possibility. High-temperature burning creates tiny particles that can travel far from their source. Soot, black carbon, fly ash, and industrial spheres can settle into sedimentary basins and become part of layers. Some forms of carbonaceous particles resist decay and can be recognized under microscopes in recent records. If a vanished civilization burned fossil fuels or biomass at enormous scale, it might leave a sudden increase in such particles. But wildfires also create charcoal and soot, and some geological intervals are rich in evidence of burning for natural reasons. The difference would have to emerge in the distribution, the chemistry, the particle types, and their association with other industrial markers. Fire alone is ancient. Industrial combustion is fire tied to extraction, machinery, and planetary-scale energy use. Metals would form another part of the underground signature. A technological society mines what natural erosion might have left locked away. It pulls copper, lead, nickel, chromium, tin, zinc, mercury, uranium, aluminum ores, rare earth elements, and many other materials from the crust, then spreads them through products, waste, emissions, landfills, water systems, and soils. A future sediment layer might show enrichments in combinations that do not match ordinary volcanic ash. Hydrothermal deposits, or eroded ore bodies. It might show lead pollution, mercury spikes, unusual alloys broken down into their elemental components, or rare metals concentrated in urban and industrial deposits. Yet this too requires caution. Earth is chemically uneven. Ore bodies exist naturally. Volcanic provinces can produce metal anomalies. Hydrothermal systems can concentrate elements without intelligence. The Silurian argument would need a pattern too complex and too globally coordinated to be easily natural. Radioactive traces are dramatic but time-limited. Nuclear technology produces isotopes and distributions unlike ordinary background radiation. In the recent human record, some radionuclides offer precise markers of nuclear testing and nuclear accidents. But over millions of years, many isotopes decay away. A civilization very ancient might leave little direct radioactivity detectable today unless long-lived isotopes, altered daughter products, waste repositories, or unusual uranium and plutonium patterns persisted under favorable conditions. Even then, natural nuclear reactors have existed on Earth, as in ancient uranium deposits where conditions once allowed self-sustaining reactions. That surprising fact is a warning. Even an apparently technological clue may sometimes have a natural counterpart if the planet is given enough chemistry, water, pressure, and time. Biological disruption could be among the most visible signals, though not the easiest to interpret. A civilization capable of global trade, agriculture, hunting, fishing, habitat destruction, pollution, and climate alteration might drive extinctions across many groups at once. It might spread favored species, reduce biodiversity, simplify ecosystems, and leave behind sudden changes in pollen, spores, bones, shells, and microfossils in marine sediments. Future observers might see shifts in plankton communities, reef collapse, acidification stress, or oxygen depletion. On land, they might see a decline in large animals, expansion of disturbance-loving plants, or unusual abundance of domesticated or commensal species. But mass extinctions have natural causes too: impacts, volcanism, climate swings, sea level changes, and ocean chemistry crises have all reshaped life. An extinction pulse proves catastrophe, not civilization by itself. Sediment itself may preserve the physical work of industry. Mining creates tailings. Cities create rubble layers. Dams trap sediment upstream and starve deltas downstream. Deforestation increases erosion. Agriculture changes soil structure. Roads and construction alter drainage. A vanished industrial civilization might leave deposits of crushed rock, glassy particles, fired materials, ceramics, concrete-like fragments, and artificial mineral assemblages over time. These could become conglomerates or unusual sedimentary horizons. Some might resemble natural breccias, volcanic deposits, storm layers, or impact debris unless examined closely. The key would be texture, composition, distribution, and repetition across many sites. This is the strange strength and weakness of the Silurian search. The strongest evidence would almost never be one miraculous object. It would be convergence, carbon, nitrogen, metals, synthetic chemistry, combustion residue, radionuclides, extinction, erosion, and strange sediments would need to gather into one narrow interval. The interval would need to be abrupt, it would need to be widespread, it would need to resist ordinary explanation. It would need to show not merely that Earth changed, but that something reorganized matter and energy in a way resembling technology. No such confirmed layer has been found for a pre-human civilization, but the exercise clarifies what people should look for, and just as importantly, what they should not mistake for proof. Beneath the stone, the truth would not announce itself in a human voice. It would arrive as numbers, ratios, grains, residues, absences, and damaged patterns. It would require patience and skepticism. It would demand that wonder and restraint stand together, because the same rock can invite imagination and punish carelessness. If civilization ever becomes geology, it stops looking like a city and starts looking like a disturbance in the planet's metabolism. That is the hidden grammar of the Silurian Hypothesis, not a search for golden ruins, but a search for the faint, stubborn fingerprints of energy use, chemistry, extinction, and time. The deeper the search goes, the more Earth begins to resemble a master forger. It can create carbon shocks without industry, metal anomalies without machines, extinction pulses without weapons, fires without factories, and strange layers without cities. This is why the Silurian hypothesis has to move carefully through the rock record. A mysterious layer is not enough. A sudden environmental crisis is not enough. Even a global catastrophe is not enough. Earth has produced upheavals so violent that, seen from far away, they might almost look like the work of a civilization powerful enough to damage its own world. But almost is the dangerous word. Natural history is full of false clues. One of the most important examples is the Paleocene-Eocene thermal maximum, often called the PETM, a rapid warming event about 56 million years ago. In the rocks, it appears as a sharp disturbance in the carbon cycle, with larger amounts of lighter carbon entering the atmosphere and oceans. Temperatures rise. Ocean chemistry changes. Some deep-sea organisms suffer severe losses. Mammals on land shift in range and body size. Sediments preserve signs of acidification and ecological stress. At first glance, for anyone thinking about industrial carbon release, the resemblance is uncomfortable. A great pulse of carbon enters the Earth system, climate warms, life responds. Yet the PETM is not evidence of an ancient civilization. The leading explanations involve natural carbon release, possibly connected to volcanism, methane, organic-rich sediments, orbital forcing, ocean circulation, or several mechanisms working together. Scholars still debate the exact trigger and sequence, but the event sits firmly within the range of Earth system processes, not technology. That distinction matters because the PETM shows how dangerous a single clue can be. If a future observer found only a carbon isotope shift, the story would remain open. Carbon can come from many places. It can come from volcanic gases, methane hydrates, thawing organic material, burning peat, altered ocean circulation, or the weathering of rocks. A civilization that burns fossil fuel could also create a carbon shift. But the shift alone cannot identify the cause. It needs companions. It needs synthetic residues, unusual metal distributions, combustion particles, biological turnover, sedimentary changes, and timing that points towards something more coordinated than a natural pulse. Without that convergence, the safer answer remains nature. Farther back in time, the end Cretaceous catastrophe offers another kind of false clue. About 66 million years ago, an asteroid strikes near what is now the Yucatan Peninsula. The impact throws dust, vaporized rock, sulfur, and debris into the atmosphere. Fires spread in many regions. Sunlight is reduced. Food chains collapse. Non-avian dinosaurs disappear, along with many marine reptiles, flying reptiles, ammonites, and countless other forms of life, in rocks around the world. A thin boundary layer preserves unusual levels of iridium-shocked quartz, tiny glassy spherules, and other evidence of impact. It is one of the most famous global markers in geology, and it is wonderfully dramatic without needing intelligence at all. To a careless imagination, a global layer enriched in rare elements and associated with extinction might look like a technological disaster. But the actual pattern tells a different story. Iridium is rare in Earth's crust and more common in some extraterrestrial material. Shocked minerals form under pressures associated with impacts or nuclear explosions. But in this case, the scale, age, crater, spherules, and global distribution all point toward an asteroid. The boundary is not a hidden war layer or a vanished industrial accident. It is the scar of celestial mechanics meeting a living planet. The impact reminds us that Earth's record can contain sudden, worldwide, chemically strange layers produced by forces completely outside civilization. Large igneous provinces create even longer and more complicated false clues. The Siberian traps, associated with the end Permian mass extinction about 252 million years ago, represent one of the most destructive volcanic episodes in Earth history. Enormous volumes of lava and volcanic gases are released over an extended interval. Carbon dioxide, sulfur gases, methane release, ocean warming, acidification, low oxygen, and toxic chemistry may all play roles in the crisis. The result is the most severe known mass extinction, devastating marine and terrestrial ecosystems. If a vanished industrial civilization is imagined as capable of poisoning atmosphere and sea, the end Permian world shows that Earth can do something similar through volcanism alone, on a terrifying scale. The end Permian event also shows how layered natural explanations can be. There may not be one simple trigger, but a cascade. Volcanism warms the climate. Warming reduces oxygen in the oceans. Ocean chemistry changes. Methane or other carbon sources may amplify the warming. Acidification stresses shell-forming organisms. Land ecosystems collapse under heat, drought, erosion, and biological disruption. Microbial processes may release toxic compounds. No single explanation fully accounts for every detail in a simple way, but the evidence does not require industry. It requires a planet capable of destabilizing itself through internal fire. Oceanic anoxic events offer a quieter but equally important warning. At several times in the Mesozoic and earlier, large parts of the oceans become depleted in oxygen, allowing dark, organic-rich shales to accumulate. These layers can be rich in carbon and sometimes associated with warming, volcanism, nutrient changes, sea level shifts, and disruptions to marine life. A world with widespread industrial fertilizer runoff and climate change might also create expanded low-oxygen waters. So the resemblance is again tempting. But ancient black shales do not point automatically to civilization. They can form when ocean circulation weakens, nutrients increase naturally, volcanic carbon warms the world, and marine basins become stratified. The sea can suffocate without factories. Even metal anomalies can mislead. Volcanic eruptions can spread ash rich in certain elements. Hydrothermal systems can concentrate metals in ways that seem almost engineered. Weathering can release elements into rivers and seas. Organic rich sediments can capture metals under low oxygen conditions. Mercury spikes in rocks may point toward volcanism rather than industry. Uranium deposits can form through natural geochemistry. Iron formations record ancient ocean and atmosphere conditions on scales far beyond human industry. The planet is not chemically bland until civilization arrives. It is restless, uneven, and inventive. Fire, too, is older than humanity. Once plants spread across land and oxygen levels allow combustion. Lightning can turn landscapes into charcoal. The fossil record contains ancient wildfire residues, charcoal layers, and soot long before any hominin tends a hearth. During periods of high oxygen, fires may become especially widespread. If a future scientist found abundant charcoal in an ancient layer, the first explanation would not be industry. It would be climate, vegetation, oxygen, lightning, and ecological setting. Industrial combustion has its own fingerprints, but burning itself is a natural planetary process. This is where many popular lost civilization claims fail. They find an anomaly and leap directly to intention. A strange stone, a surprising metal concentration, a melted surface, an ancient catastrophe, a myth of fire from the sky. A map that seems unusual, a fossilized track, or a layer of ash becomes, in the wrong hands, proof of a hidden world. But science does not work by filling uncertainty with the most exciting story. It asks whether the claim fits all the evidence better than natural explanations do. It asks whether the object is correctly dated, whether the context is secure, whether the interpretation is reproducible, and whether simpler processes can account for the find. Most alleged traces of pre-human technology collapse under those tests. Many are misdated, misidentified, taken from poor context, or explained by ordinary geology. The Silurian hypothesis survives because it does not make that leap. It does not say every strange layer is suspicious. It says the opposite Earth has many ways to make strange layers, so an industrial signal would need to be extraordinary in its pattern, not just in its drama. It would have to stand apart from volcanism, impact, anoxia, wildfire, climate oscillation, erosion, ocean chemistry, and biological evolution. It would need to look less like one disaster and more like a whole system of extraction, energy use, waste, atmospheric change, ecological reshuffling, and artificial chemistry compressed into the rocks. That is why the old catastrophes are not distractions from the mystery. They are the training ground for reading it correctly. They teach caution. They show how powerful nature can be without intelligence. They remind us that a planet does not need cities to change its climate, darken its skies, poison its seas, or erase whole branches of life. And they leave the deeper question sharper than before. If a civilization before humanity ever did scar the Earth, its signal would have to rise above a background already crowded with natural catastrophes. It would have to be stranger than a volcano, stranger than an asteroid, stranger than a suffocating ocean, and clear enough to survive the planet's long habit of making false clues look almost true. A recognizable artifact is one of the most comforting things in the study of the past. It gives the mind something to hold. A blade still has an edge. A bowl still has a curve. A wall still has a line that nature rarely makes by accident. Even when broken, an artifact carries intention in its shape. It tells the viewer that someone chose, struck, carved, fired, polished, poured, joined, or arranged material for a purpose. That's why the idea of an ancient machine buried in deep rock feels so compelling. It would seem to cut through all uncertainty. No argument over isotopes, no debate over climate feedback. No need to infer a civilization from chemistry. Just an object, impossible to mistake. But deep time is hardest on exactly that kind of evidence. An artifact is not only matter, it is matter in a pattern. A bronze tool is meaningful because copper and tin remain alloyed in a shaped form. A gear is meaningful because teeth, axle, spacing, and context remain together. A circuit board is meaningful because metals, ceramics, polymers, etched pathways, and components still preserve their relationships. A city is meaningful because streets, foundations, drains, hearths, workshops, waste pits, and human activity remain in a readable arrangement. Geological time does not need to destroy all the material. It only needs to destroy the arrangement. Once the pattern is gone, the evidence may no longer look like intelligence. It may become a stain, a mineral concentration, a pebble, a vein, a rusted lump, or sediment with an unusual chemistry. The first enemy is exposure. Objects left at the surface enter the active world of weather. Sunlight breaks chemical bonds. Oxygen reacts with metals and organic compounds. Rainwater dissolves, transports, and recrystallizes minerals. Wind abrades exposed surfaces grain by grain. Temperature changes expand and contract materials. Salt enters cracks and forces them wider. Roots pry apart stone and pavement. Microbes feed on organics and alter chemistry. Animals burrow, trample, scatter, and chew. Fire burns, floods move, landslides bury and grind, and glaciers scrape landscapes down to bedrock. A surface artifact must quickly become buried or protected if it is to have any chance of long survival. Most things never get that chance. Burial seems safer, and often it is, but burial is not the same as preservation. Underground, objects enter another set of chemical trials. Groundwater carries dissolved minerals, acids, salts, and oxygen depending on local conditions. Iron corrodes into oxides and hydroxides. Copper forms carbonates, sulfides, and other corrosion products. Glass can hydrate and flake. Ceramics may survive well, but their surfaces and context can be damaged. Organic materials such as wood, leather, cloth, paper, and plant fiber usually decay unless they're protected by dryness, freezing, waterlogging without oxygen, charring, or unusual chemistry. Plastics and synthetic materials follow complex paths, breaking, leaching, fragmenting, or transforming. The evidence remains incomplete because preservation depends not on cultural importance, but on chemistry, moisture, temperature, microbes, pressure, and luck. Then pressure begins to matter. Sediment layers accumulate. A buried city, landfill, mine, or industrial site may be compacted under the weight of later deposits. Voids collapse. Structures deform. Objects break. Fluids move through pore spaces and replace original materials. Over longer spans, sediment hardens into rock. The process can preserve impressions, outlines, and chemical traces, but it can also flatten, distort, dissolve, or recrystallize what was once recognizable. A buried tire might not remain a tire. A buried building may become a mixed layer of mineral fragments. A machine may become a cluster of corrosion minerals and trace metals. The more complex the object, the more vulnerable it is to losing the relationships that made it an object. Heat adds another threshold. As rocks are buried deeper, temperatures rise, chemical reactions accelerate. Organic molecules break apart. Minerals change. Under metamorphism, heat and pressure can transform whole rock bodies. Shale becomes slate, then schist. Limestone becomes marble. Sandstone becomes quartzite. Sedimentary textures can be partly or entirely erased. Fossils may be distorted or destroyed. Any artifact caught in such a process would struggle to retain identity. Metals might melt, migrate, recrystallize, oxidize, or react with surrounding minerals. Ceramics and glass might survive as strange inclusions or be altered beyond recognition. A civilization buried in sediments that later undergo metamorphism may leave little more than geochemical oddities, if even that. Plate tectonics is the great long-term destroyer. Continents drift, collide, split, and deform. Ocean basins open and close. Mountain ranges rise where crust is compressed, and those mountains then erode into rivers and seas. Faults cut through old layers. Volcanism buries landscapes under lava and ash. Subduction carries oceanic crust down into the mantle, recycling it into Earth's interior. This matters because much of Earth's surface is not ancient. The ocean floor, which covers most of the planet, is constantly renewed on geological timescales. Very old ocean crust is rare compared with continental crust. If a hypothetical civilization lived along coasts, islands, shallow seas, or oceanic plates that were later subducted, much of its physical world could be completely gone, not merely hidden from discovery, but consumed by the planet. Continents preserve older rocks, but not evenly. Some continental interiors hold rocks billions of years old. Other regions are repeatedly buried, deformed, eroded, flooded, uplifted, glaciated, or intruded by magma. A city built on a stable craton would have better odds than one built on a subduction margin, delta, volcanic island arc, or active mountain belt. But better does not mean good. The city would still need to be buried in the right way, protected from erosion, spared intense metamorphism, and later exposed without being destroyed before discovery. The chain of luck is long and unforgiving. Sea level repeatedly rewrites the margins of continents. During ice ages, water is locked in ice sheets and sea levels fall, exposing continental shelves. During warm periods, sea levels rise and drown coastal plains. Since many civilizations favor coasts and rivers, their most important settlements may lie in zones that are especially vulnerable to repeated flooding, erosion, sediment movement, and burial. The present shoreline is only one temporary line among many. A port can become inland sediment, drowned seabed, eroded cliff, or subducted margin depending on where it sits and how much time passes. The familiar map is a poor guide to the deep past. Even extraordinary preservation can mislead by its rarity. Pompeii preserves a Roman town because volcanic catastrophe buried it quickly. Waterlogged sites can preserve wood and textiles that would normally vanish. Dry caves can hold delicate organic remains. Frozen ground can preserve bodies, tools, and DNA across thousands of years. But such preservation feels miraculous precisely because it is unusual. It cannot be assumed for entire civilizations, especially across millions of years. A future investigator cannot rely on finding the equivalent of a perfect buried city from the age of dinosaurs or earlier. What survives in the record suggests that rare windows may open, but most landscapes close. This is also why claims about objects found in coal, stone, or ancient strata require extreme caution. If a hammer, chain, screw, vase, or carved object is said to come from rock millions of years old, the question is not only what the object looks like, the question is where it was found, who found it, whether the context was documented, whether the surrounding rock truly formed around it, whether it entered a crack or concretion later, whether the dating applies to the object or only to nearby material, and whether natural processes can produce similar shapes. Many famous out-of-place artifacts lose their mystery when context is examined. Some are modern objects trapped in mineral deposits. Some are natural formations misread as manufactured. Some are poorly documented. A dramatic object without secure context is not a rewrite of Earth history. It is a warning about how badly people want the past to surprise them. The Silurian hypothesis does not depend on these artifacts, and that is one reason it remains intellectually serious. It understands that if an older technological species existed, recognizable objects would be unlikely to provide the first evidence after tens of millions of years. The better search would begin with broad, durable, repeated signals. Still, the near absence of artifacts matters. If a civilization were recent in geological terms, within the last few 100,000 years or even a few million years, some physical traces might be expected in favorable places. The farther back the claim moves, the less reasonable that expectation becomes. but the more difficult the claim becomes to prove. Time protects the possibility and destroys the evidence at the same time. So the artifact becomes almost tragic. It is the proof people want most, and the proof deep time is least likely to grant. A machine can vanish as a machine while its metals remain. A city can vanish as a city while its rubble enters a sedimentary layer. A road can vanish as a road while its crushed stone becomes part of a deposit. The object dies when the pattern dies. If there is a message in this, it is not that lost civilizations are hiding everywhere. It is that material memory is fragile, and human confidence in objects is shaped by the shortness of human time. Deep time does not preserve intention kindly. It grinds intention down until only chemistry, texture, and chance remain. The age of dinosaurs seems, at first, like the perfect hiding place for a vanished intelligence. It is distant enough to be strange, close enough that many rocks still survive, and rich enough in life that imagination naturally begins to wander. For more than 160 million years, dinosaurs dominate many terrestrial ecosystems. Forests spread across warm continents. Inland seas flood lowlands. Giant sauropods move through conifer woodlands. Predators leave three-toed tracks in mud that hardens into stone. Small feathered animals dart through branches. Crocodile relatives haunt rivers. Pterosaurs cross the sky. Marine reptiles hunt in oceans where ammonites coil through the water like living ornaments. It is a world deep enough to feel unreachable, yet not so deep that all its evidence is gone. Fossil bones, eggs, footprints, nests, pollen, leaves, shells, teeth, burrows, and trackways still rise from Mesozoic rocks. If an intelligent species ever flourished there, the mind wants to believe some clue should have escaped the destruction. But the dinosaur world is also a lesson in how little even an abundant world may leave behind. Dinosaurs are famous not because fossils are common, but because the fossils that survive are spectacular. For every dinosaur skeleton in a museum, countless animals died without preservation. Their bodies were eaten, scattered, rotted, weathered, trampled, or washed away. Many lived in environments where burial was unlikely. Many bones were buried and later destroyed before discovery. Entire populations vanish from the record while other groups are overrepresented because they live near rivers, floodplains, lakes, deltas, or deserts where sediment could cover remains quickly. The Mesozoic is not a continuous film. It is a damaged archive, with some pages beautifully illustrated and others missing altogether. This matters because intelligence does not automatically become fossil evidence. If a hypothetical intelligent species lived in the Mesozoic but never industrialized, its traces might be extraordinarily difficult to distinguish from the ordinary record of animal behavior. Tool use without durable tools could disappear almost completely. Wood, fiber, hide, plant cordage, feathers, resins, and soft materials rarely survive across tens of millions of years. Even stone tools would require context, repetition, and recognizable shaping to be identified as technology rather than broken rock. If the beings used fire, evidence would need to be separated from natural wildfire charcoal, which is already part of ancient terrestrial records. If they built temporary shelters, they would almost certainly vanish. If they lived mostly in forests, uplands, wetlands, or coasts, their chances of leaving a readable archaeological layer would be poor. The fossil record also complicates the search for the makers themselves. Paleontologists do not possess every species that ever lived. New dinosaurs continue to be described because the record remains incomplete. Some lineages are known from a handful of bones, some from teeth, some from footprints before skeletons are found, or skeletons without enough soft anatomy to reveal how they behaved. Intelligence would not necessarily leave an obvious mark on bone. Brain size can sometimes be estimated from skulls, and sensory abilities can be inferred in cautious ways. But behavior is more elusive. A creature can be socially complex, visually alert, dexterous, and adaptable without leaving a fossil that announces civilization. What survives in the record suggests bodies more readily than minds. That does not mean any dinosaur civilization is likely. No evidence supports it. No confirmed Mesozoic layer contains the combined chemical, industrial, and biological pattern that would point toward technology. No secure artifacts, mines, synthetic residues, alloys, cities, roads, or engineered deposits have been found in dinosaur age strata. The known story remains one of non-human ecosystems, not hidden states or machines. But the absence becomes more interesting when the scale is examined honestly. If an intelligent species had arisen and remained local, or used mostly biodegradable materials, or lasted only a short time, its chance of being seen might be extremely small. If it became globally industrial, however, the expectation would change. It should disturb more than a campsite. It should touch sediment, atmosphere, oceans, metals, and life. The Mesozoic world is especially useful because it forces the difference between intelligence and industry. Human civilization becomes geologically loud not simply because humans are intelligent, but because humans burn fossil carbon, mine, manufacture, farm at enormous scale, move species, and alter global cycles. A clever dinosaur-like animal that makes nests, communicates richly, uses simple tools, and solves problems might be almost invisible after deep time. A dinosaur industrial civilization should be harder to hide, not because its buildings would remain, but because its activity would likely produce wider planetary signals. The Silurian Hypothesis is most interested in that second case. It asks not whether some ancient animal had a mind, but whether a technological society could rise, burn, alter, and vanish without leaving a detectable scar. There is also the problem of where such a species might have lived. Many human settlements favor coasts, rivers, floodplains, and fertile lowlands. Mesozoic coastlines were not today's coastlines. Seas rose and fell. Continental interiors flooded and drained. Sediments accumulated in basins that were later uplifted, eroded, or buried. Oceanic crust from much of the Mesozoic has been recycled by plate tectonics, and even continental margins have been repeatedly reshaped. If a civilization concentrated on low coastal plains or islands, much of its physical setting could be lost, transformed. Yet continental rocks from the Mesozoic still exist widely enough that a truly global industrial signal would be expected to leave some distributed trace. The evidence remains incomplete, but not empty. One lesser-known difficulty is that the Mesozoic record can preserve exquisite behavior while still failing to preserve broader context. Dinosaur nesting grounds reveal reproductive habits. Trackways show movement, speed, herd behavior, and interactions with mud, shorelines, or riverbanks. Feather impressions reveal texture and display. Stomach contents, bite marks, healed injuries, and bone beds reveal feeding, trauma, drought, flood, and mass death. These details are intimate, almost cinematic. Yet they are scattered windows. They show that preservation can be astonishing under the right conditions, but they also show how selective it is. The record can keep the footprint of one animal crossing wet sediment and lose an entire forest community nearby. It can preserve a feather and erase a coastline. The end of the dinosaur world sharpens the point. The asteroid impact at the end of the Cretaceous leaves a global boundary layer, a mark far more durable than most individual bodies or landscapes. That layer is visible because the event is sudden, widespread, and chemically distinctive. It shows what a planet-scale signal can look like. If an industrial civilization had existed near that time and left a comparable global disturbance, scientists would look for it as a pattern across rocks of the same age. Instead, the boundary points toward impact, fire, darkness, climate disruption, food web collapse, and the extinction of non-avian dinosaurs, followed by the survival and radiation of birds, mammals, and many other lineages. The catastrophe is enormous, but it does not need civilization. This creates a quiet boundary around speculation. The dinosaur world is vast enough to remind us that Earth has hosted long experiments in life before humans. It is incomplete enough to humble any claim that every possibility is visible, but it is also well studied enough that extraordinary claims cannot simply hide behind mystery. If humans were not the first civilization, the proof would need to be stronger than absence, stronger than imagination, and stronger than a creature's lost potential. It would need to rise from the rocks with the stubborn clarity of a real signal. Until then, the Mesozoic remains not a buried empire, but a living world turned to stone in fragments immense, alien, partly knowable, and silent in exactly the way deep time is usually silent. The Silurian Hypothesis reaches its most important limit at the point where imagination wants to run fastest. It can show that evidence is fragile. It can show that cities decay, coastlines move, ocean crust is recycled, and artifacts lose their meaning when their patterns are destroyed. It can show that a civilization old enough and unlucky enough might leave only indirect traces, perhaps no recognizable objects at all. But it cannot turn that possibility into proof. It cannot take the difficulty of finding evidence and use that difficulty as evidence itself. This is the narrow line that keeps the idea scientific. The hypothesis opens a door, but it does not allow anything at all to walk through it. That line matters because deep time can become a shelter for almost any claim if caution is abandoned. A lost empire can always be moved farther back. A missing artifact can always be said to have eroded away. A vanished city can always be placed on subducted ocean crust or drowned continental shelves. A lack of inscriptions can be explained by decay. A lack of bones can be explained by poor fossilization. Each explanation may be possible in isolation, but together they can become unfalsifiable. And an unfalsifiable story is no longer a scientific explanation. It becomes a story protected from evidence by the very absence it is supposed to explain. The strength of the Silurian hypothesis is that it does not ask for belief. It asks for criteria. What would count as a signal? What kinds of signals could survive? How would those signals differ from volcanism, asteroid impacts, ocean anoxia, natural climate swings, wildfire, hydrothermal chemistry, or ordinary biological turnover? How sharply would they need to appear in the rocks? How widely would they need to be distributed? What combination of carbon, nitrogen, metals, synthetic chemistry, extinction, erosion, combustion residue, and sedimentary change would be strange enough to require a technological cause? These questions do not prove an earlier civilization. They make the absence of proof more precise. This precision is valuable because science often advances by learning how to recognize what it does not know. The rock record is incomplete. but it is not meaningless. Fossils are rare, but paleontology still reconstructs vanished worlds. Ancient climates are indirect, but isotope chemistry, sediments, microfossils, minerals, and models still reveal patterns. Archaeology works with fragments, but fragments can be powerful when context is secure. The evidence remains incomplete. Yet incompleteness does not erase standards. A damaged archive can still rule out many stories. It can still show when a claim requires more than the record provides. For a pre-human industrial civilization, the standards would be very high. A single strange object is not enough if its context is uncertain. A single chemical anomaly is not enough if natural processes can explain it. A sudden warming event is not enough if volcanism, methane release, or orbital factors fit the evidence. A mass extinction is not enough if impact or climate disruption explains the pattern. Even a suite of unusual traces would have to be tested against every plausible natural process before intelligence could be proposed. The order of explanation matters. Earth has the first right of reply. Only after geology has failed in a disciplined way would technology become a serious interpretation. This is why the hypothesis is less about finding a hidden past than about testing the blindness of the present. Human beings are used to being the only technological species they know. That may be true, and all available evidence says it is true for Earth so far. But the habit of seeing civilization through buildings, writing, and artifacts may become misleading when applied across millions of years. The Silurian Hypothesis forces a different kind of search image. It asks researchers to imagine civilization not as a ruin, but as a planetary metabolism. Energy enters, carbon moves, nitrogen shifts, materials are extracted and concentrated, waste spreads, species vanish, multiply, and travel. Sediments change. This does not make ancient industry likely. It makes the idea testable in geological language. There is a quiet irony in that. The hypothesis is often misunderstood because its title sounds like a suggestion of ancient beings. Yet its actual effect is often skeptical. It makes many spectacular claims look weaker, not stronger. If someone claims that a lost civilization existed a few 100,000 years ago, then the archaeological record should be asked for camps, tools, bones, hearths, landscapes, genetic traces, or ecological impacts. If someone claims an industrial civilization existed tens of millions of years ago, then the geological record should be asked for global chemical disturbance, unnatural materials, extraction signatures, and biological consequences. Moving a claim backward in time does not free it from evidence. It changes the kind of evidence required. The hypothesis also has a limit in scale. A small intelligent species with modest technology might leave almost nothing, especially if it lived briefly, locally, and used mostly perishable materials. Such a possibility may be difficult to disprove completely, but it also may be impossible to confirm. It would remain a shadow at the edge of knowability. Interesting perhaps, but scientifically weak unless some trace appears. A global industrial civilization is different. Its activities should be harder to hide. It might lose its cities, but it should leave broader disturbances. If it leaves neither artifacts nor geological signals, then the claim has very little left to stand on. This distinction keeps the mystery grounded. The absence of evidence does not always prove absence, especially in deep time, but it still matters. Absence has weight when the expected signal should be large. If a global industrial civilization burned fossil fuels, mined widely, created synthetic chemistry, caused extinctions, and altered climate. Future geologists would expect at least some strange combination of signs. No such confirmed pre-human signal has been identified. That does not mean scientists have read every rock perfectly. It means the responsible conclusion remains that humans are the only known technological civilization Earth has produced. The word known does important work. It is not a loophole for fantasy. It is an honest boundary. Known means supported by evidence strong enough to survive scrutiny. Known means not merely imaginable, not merely emotionally compelling, not merely hidden in a gap. Known means the claim has passed through context, dating, comparison, and alternative explanations. In the deep past, known is difficult to earn, but difficulty is not unfairness. It is the price of speaking about lost worlds with discipline. The Silurian Hypothesis therefore becomes a lesson in scientific humility from both directions. It humbles certainty by showing how much the planet can erase. It humbles speculation by showing how much evidence a serious claim must bear. It allows wonder, but it does not let wonder become a substitute for proof. It allows the possibility that the record may be biased, but it does not turn bias into a blank canvas. It makes the silence deeper, but not empty enough to write anything on it. At this point, the mystery becomes less about a supposed lost species and more about the relationship between existence and detectability. Something can happen and leave little trace. Something can leave a trace and still be misread. Something can look strange and still be natural. The past is not obligated to be obvious, and the present is not entitled to easy answers. What remains is a disciplined unease, a recognition that Earth may not preserve every story, but also that science cannot accept a story merely because the Earth is capable of forgetting. Around every real mystery, a second landscape tends to grow. It is not made of stone, sediment, isotopes, or fossils, but of stories repeated until they feel older than they are. A strange photograph becomes evidence of a vanished world. A natural rock shape becomes a carved machine part. A myth becomes a historical report. A missing layer becomes a cover-up. An ancient disaster becomes a war. A monument built by human hands becomes too impressive for its builders, and so the builders are quietly replaced by aliens, giants, survivors from Atlantis, or a forgotten race with technologies always just beyond verification. The Silurian hypothesis often gets pulled toward that landscape because its central question sounds dangerous. Could there have been a civilization before humans? But the real hypothesis and the popular mythology around it are not the same thing. One is a careful test of geological detectability. The other often begins with a conclusion and goes looking for shadows to support it. The difference matters because ancient people have often been robbed twice. First, time damages their work. Then modern imagination decides they could not have done it. The pyramids, the ziggurats of Mesopotamia, the stone circles of Western Europe, the cities of the Maya, the earthworks of North America, the temples of Angkor, the statues of Rapa Nui, the walls of the Andes, the Indus cities, the megaliths of many regions, all become vulnerable to a strange kind of disbelief. Their very grandeur is used against them. Instead of seeing organization, skill, labor, experiment, religious meaning, engineering patience, and generations of accumulated knowledge, fringe stories often replace known human achievement with lost super civilizations or visitors from the stars. This may sound like wonder, but it can become a failure to respect the real capacities of ancient societies. That does not mean every archaeological question is solved. Many sites still hold uncertainty. Scholars still debate how labor was organized, how knowledge moved, how rituals changed, how trade routes developed, how early cities managed water, how states formed, why some settlements were abandoned, and how different cultures understood the worlds they built. The evidence remains incomplete, and that incompleteness is part of what makes the ancient past so compelling. But an incomplete answer is not the same as an invitation to discard the evidence that does exist. A missing detail about construction does not prove levitation. A symbolic carving does not prove a machine. A mythic flood does not prove a global technological collapse. A strange alignment does not prove knowledge beyond the culture that built it. Ancient aliens are one of the clearest examples of this confusion. The claim usually begins with a genuine marvel, a monument aligned to the sky, a stone transported across distance, a carving that looks unusual to modern eyes, a myth describing beings from above, a structure built with remarkable precision. Then the explanation leaps away from the ground. It assumes that ancient people lacked the intelligence, tools, social organization, or patience required. But archaeology repeatedly shows that human communities can achieve extraordinary things with simple materials when they possess time, skill, planning, and shared purpose. Wood, rope, sledges, ramps, levers, boats, water, packed earth, stone tools, copper tools, labor crews, seasonal work, and practical experimentation can produce results that look impossible only when the builders are imagined as primitive. The surprise often comes not from the past, but from modern underestimation of it. Lost advanced civilizations present a subtler problem. Some versions imagine a human society before the known early cities, destroyed by flood, comet, climate shift, or war, leaving memories scattered as myths and monuments. It is true that the end of the last ice age transformed coastlines and landscapes. Sea levels rose dramatically, drowning coastal plains where people may have lived. Climate changes altered migration, hunting, foraging, and early farming. Sites beneath today's shallow seas may indeed preserve important evidence about late Ice Age and early Holocene communities. Archaeologists do not dismiss this possibility. They actively study submerged landscapes, drowned settlements, ancient coastlines, and the ways rising seas erased parts of human experience. But this is very different from proving a globe-spanning industrial civilization before agriculture. Complex hunter-gatherer societies, early ritual centers, coastal settlements, and lost villages are plausible and increasingly important. Laser weapons, anti-gravity machines, and vanished world empires are not supported by the evidence. The Silurian hypothesis also gets misused because it sounds as if it licenses any hidden past deep enough to escape detection. In reality, it does nearly the opposite. It raises the standard. If someone claims there was a pre-human industrial civilization, then the question becomes geological. Where is the carbon signal? Where are the industrial residues? Where are the unusual metal enrichments? Where are the synthetic compounds or their altered descendants? Where is the extinction pattern tied to extraction, energy use, and global ecological disturbance? Where are the sedimentary signs of a species moving matter at planetary scale? If the proposed civilization is said to be advanced enough to transform Earth, then its absence from the record becomes harder, not easier, to explain. This is why many supposed out-of-place artifacts remain weak evidence. Objects said to be too old for their form often arrive with poor documentation, uncertain discovery conditions, or dating that applies to surrounding material rather than the object itself. Concretions can grow around recent objects and make them appear ancient. Natural mineral formations can mimic screws, gears, tools, or worked stone. Erosion can shape rock into forms that look intentional from one angle. Fossils can be misidentified. Modern objects can enter old deposits through cracks, mining, excavation, burrows, or disturbance. No single explanation fully accounts for every claim in the popular catalogue, but the repeated pattern is revealing when context is secure and specialists examine the material. The extraordinary interpretation usually weakens. There is a psychological reason these stories persist. A hidden advanced past makes the world feel larger, stranger, and more dramatic. It turns ruins into clues, disasters into warnings, myths into reports, and geological silence into conspiracy. It gives the viewer the thrill of standing near forbidden knowledge. Real science offers a different thrill, quieter but more durable. It does not promise that every mystery has a secret civilization behind it. It shows that the known world is already stranger than the shortcut. Continents move, oceans vanish, mass extinctions reset life. Human beings emerge late from a branching family of hominins. Ice sheets bury landscapes. Deserts turn green and then dry again. Cities rise from mud, river silt, and grain storage. Entire writing systems are lost and recovered. DNA rewrites migration stories. Rocks preserve the breath of vanished atmospheres. Nothing in that requires invention to feel immense. The genuine mystery is not diminished by rejecting unsupported claims. It becomes cleaner. Humans are the only known civilization on Earth, and the evidence for that remains strong. Known civilization appears in the recent Holocene, after long developments in human biology, culture, migration, toolmaking, art, symbolism, agriculture, and settlement. The earliest cities and states are not sudden miracles dropped into emptiness. They are the visible crest of a much longer human wave. Before them lie villages, camps, ritual places, seasonal movements, domestication, experimentation, failure, adaptation, and memory carried without writing. The real story is not less impressive because it is human. It is more impressive because it is human. At the same time, the Silurian Hypothesis keeps one legitimate door open, not for fantasy, but for humility. It reminds us that Earth's record is selective. It reminds us that absence must be interpreted carefully. It reminds us that an industrial civilization would become most visible not as a palace of gold, but as a disturbed layer in planetary chemistry. That idea does not validate ancient aliens or hidden empires. It disciplines the search. It says that if the past contains something extraordinary, it must still leave extraordinary evidence in the right form. Wonder survives, but it has to stand where evidence can reach it. So the real boundary is not between mystery and skepticism. It is between mystery that deepens the evidence and mystery that replaces it. The first kind belongs to science, archaeology, geology, and careful history. The second kind belongs to stories that may entertain but cannot carry the weight of the past. The Silurian Hypothesis is powerful because it lives on the difficult side of that boundary. It allows the mind to imagine a vanished world, then asks what the rocks would actually say. And when the rocks remain silent, it does not force them to speak. It listens harder. The earth does not testify like a witness in a human court. It does not remember motives. It does not preserve names. It does not explain whether a species was wise, violent, frightened, curious, or doomed by its own cleverness. Its testimony is colder and older than that. It speaks through clay, ash, limestone, shale, ice, pollen, shell chemistry, fossil teeth, buried soils, magnetic minerals, impact glass, reef collapse, coal seams, desert dust, and the sudden absence of creatures that were once everywhere. To listen to Earth is to accept a language without intention. The planet records transformation, not meaning. It keeps the wound, but not the cry. That is why the Silurian hypothesis eventually becomes less a search for ruins than a meditation on what kind of witness a planet can be. If something enormous happens, Earth may record it, but it records it in Earth's own terms. A forest does not become a story about trees reaching toward light. It becomes coal, pollen, spores, leaf impressions, carbon, and sediment. A vanished ocean does not become a map of waves and creatures. It becomes limestone, evaporates, microfossils, isotopes, and minerals that formed underwater long gone. A mass extinction does not become a book of deaths. It becomes a boundary where certain fossils become rare, then disappear, while other forms endure or arrive. The record is powerful, but it is never complete. It gives evidence, not memory. Consider the Great Extinction boundaries. They are among the clearest scars in Earth history, but even they do not preserve full experience. The Permian extinction does not show the terror of an animal failing to find oxygen in warming seas. It shows a collapse in marine diversity, altered carbon cycles, volcanic signatures, changing sediments, and ecosystems struggling through heat and chemical stress. The Cretaceous boundary does not preserve the darkness falling over every landscape in a single human-style scene. It preserves iridium, shocked minerals, glassy spherules, soot, disturbed ecosystems, and the disappearance of many fossil lineages. These are not weak records. They are immense records, but they are abstracted by time. They show the shape of catastrophe after the living world has been compressed into chemistry and absence. Climate leaves a similar witness. Ancient warming events appear in isotope shifts, fossil migrations, ocean acidification, clay minerals, soil changes, and altered patterns of erosion. Ice ages leave scraped bedrock, moraines, drop stones, loess, sea level changes, oxygen isotopes in marine shells, and traces of vegetation retreating and returning. Greenhouse worlds leave palm-like plants at high latitudes, crocodilian relatives in places that later freeze, and rocks formed under seas where deserts now stretch. Earth's climate history is not written as a sequence of weather reports. It is written as rearrangement. A warmer ocean changes the chemistry of shells. A wetter world changes rivers. A drier world changes dust. A glaciated world grinds mountains and lowers seas. Each transformation leaves clues, and each clue must be interpreted through uncertainty, comparison, and context. The fossil record is Earth's witness to life, but it too speaks unevenly. Some organisms are preserved in abundance because they have hard shells, live in sediment-rich environments, or die where burial is rapid. Others vanish almost entirely because their bodies are soft, their habitats erosive, or their remains chemically fragile. Whole ecosystems can be represented by a handful of bones, while tiny marine organisms may leave vast accumulations of shells on the seafloor. This unevenness does not make paleontology unreliable, it makes it careful. Scientists learn to read bias as part of the evidence. They ask why something is present, why something is absent, what environments are sampled, What rocks survived, and what later processes destroyed? What survives in the record suggests life's history, but always through a filter. A technological civilization would pass through the same filter. Earth would not preserve it because it was meaningful. It would preserve only those parts that entered durable processes. If its buildings stood on an eroding upland, they might vanish. If its waste collected in an anoxic basin, some chemical traces might endure. If its industry changed the atmosphere, oceans, and biosphere, those changes might become visible across many environments. If it produced only local effects, it might leave nothing that could be recognized after millions of years. The planet's testimony would not be fair in a human sense. It would not reward intelligence. It would reward scale, chemistry, burial, and luck. This is also why Earth can make the ordinary look mysterious. A thin clay layer at a boundary may represent fallout from an asteroid impact. A black shale may represent a suffocating sea. A red bed may represent oxidized sediment laid down under ancient conditions. A salt deposit may mark an evaporated sea. A coal seam may mark a swamp forest buried and compressed. A band of volcanic ash may allow precise dating across continents. None of these layers carries a label. Their meaning emerges only when many clues are brought together: mineralogy, fossils, geochemistry, radiometric dating, sediment structures, regional comparison, and physical models. Scholars still debate details because the witness is not verbal. It must be cross-examined by methods, not merely admired. The strangest part is that Earth sometimes preserves the smallest things better than the grandest. A microscopic shell can record the temperature of an ancient ocean more clearly than a mountain records the civilizations that pass beside it. A pollen grain can reveal a vanished forest. A tiny magnetic mineral can show where a continent once sat relative to the poles. A chemical ratio in a cave deposit can suggest rainfall changes over thousands of years. A single layer of ash can synchronize distant landscapes. A tooth can reveal diet, migration, and climate. A footprint can preserve a moment of movement long after the animal itself is gone. The witness is not always broad and blunt. It can be delicate, but only when conditions allow delicacy to last. This gives the planet an almost paradoxical character. It is ruthless and generous at once. It destroys nearly everything, yet preserves enough to reconstruct worlds no human ever saw. It grinds mountains down and keeps ripple marks from vanished shores. It subducts ocean floors and preserves zircons older than continents in their present form. It erases bodies and keeps burrows. It crushes forests and keeps their carbon. It forgets names and remembers atmospheres. For a species trying to understand whether it is alone in Earth's technological history, this is both hopeful and sobering. Earth's silence is meaningful, but not simple. Its memory is real, but not complete. So when the question returns, were humans the first civilization on Earth, the witness does not answer with drama. It answers with the record available so far. No confirmed pre-human industrial layer has emerged. No combination of ancient synthetic chemistry, extraction signatures, fossil fuel combustion, artificial radionuclide patterns, industrial sediments, and unexplained global ecological disturbance has forced science to recognize another civilization. The known evidence points to humans as the first technological species visible in Earth history, but the same record also teaches caution. The planet's memory has gaps. It preserves scars better than stories. It may reveal transformation while hiding identity. It may say that something happened and still refuse to say who, if anyone, made it happen. That refusal is not emptiness. It is the nature of deep time. Earth is not a guardian of human-style meaning. It is a witness made of rock and process, a witness that speaks in damaged layers and durable consequences. The Silurian Hypothesis asks us to respect that witness without forcing it into fantasy. It asks us to see the planet as both archive and destroyer, both evidence and erasure. And under that view, the past becomes larger, not because hidden empires must be waiting there, but because even the worlds we know existed are already half lost, surviving only where stone, chemistry, and chance allowed them to leave a trace. What humans may leave behind is not the same as what humans hope will remain. This is one of the quietest and most unsettling lessons of the Silurian Hypothesis. Civilization spends enormous effort making meaning visible. It raises monuments, names, streets, stores, archives, builds museums, carves memorials, launches records into space, preserves bodies, protects documents, and teaches children or inherits stories. Yet the future does not inherit everything equally. A nation may vanish while a landfill endures. A library may burn while a layer of industrial ash settles safely into lake mud. A cathedral may collapse while the chemistry of the atmosphere carries its age into stone. The things most carefully made to speak may fall silent, while the things most casually discarded become the strongest testimony. Seen from the present, humanity's largest structures appear almost geological already. Megacities spread like artificial reefs across plains and coasts. Concrete dams hold back rivers with the mass of cliffs. Open pit mines descend in terraces visible from the air. Highways cross mountain passes as deserts in lines too regular for nature. Tunnels pierce rock. Ports dredge harbours. Farms replace forests with grids. Reservoirs drown valleys. Waste sites accumulate plastics, metals, glass, ceramics, food remains, chemical residues, construction debris, and the bones of animals raised in extraordinary numbers. But the future will not see all of this as humans see it. It will see what survives burial, erosion, chemical change, and later exposure. The monument of the human age may not be the skyline. It may be the layer underneath it. Concrete is one of the obvious candidates for a human geological signature. It is produced in enormous quantities and used everywhere from towers and bridges to roads, ports, drains, foundations, seawalls, bunkers, and ordinary houses. In the short term, concrete can be durable. In the long term, it breaks, reacts, weathers, and joins sediment. Reinforced concrete has internal weaknesses because steel corrosion can split it from within. Yet fragments of concrete, brick, asphalt, ceramic tile, glass, and fired clay may enter rubble deposits and become part of future conglomerates. Urban areas may create unusual sedimentary layers rich in manufactured rock-like material. A future geologist may not see a building, but may see a strange deposit of angular fragments, lime-rich cement, industrial minerals, glass, metal oxides, and artificial textures spread across what was once a city basin. Landfills may become even stranger archives. They contain the accidental inventory of civilization packaging, electronics, clothing fibers, toys, food waste, batteries, medical waste, paper, metals, plastics, ceramics, construction material, and the remains of animals and plants carried through global supply chains. Under some conditions, landfills may decay, leak, collapse, burn, or be eroded away. Under others, parts may be buried, compacted, mineralized, and sealed. What survives in the record suggests that landfills could become concentrated pockets of unnatural material diversity. They may contain plastics in various stages of degradation, unusual metal mixtures, rare elements from electronics, glass fragments, altered organic matter, and the bones of domesticated animals. They are not noble monuments, but geology does not ask whether a deposit is noble. Mining may be one of humanity's most durable physical signatures because it rearranges the crust itself. Open pits, underground workings, tailings piles, spoil heaps, quarry faces, and tunnels mark the movement of rock on a scale far beyond ordinary animal behavior. Some voids will collapse, some pits will fill with water, sediment, or vegetation. Some tailings will erode into rivers, some mines will be buried under later deposits. Over deep time, the sharp geometry may soften or vanish. But the geochemical disturbance can remain, or minerals once concentrated underground are spread across landscapes. Waste rock exposes minerals to oxygen and water, creating chemical drainage. Elements that were once locked away enter soils and sediments. A future observer may not find a mining company's name, but may find a pattern of extraction and dispersal difficult to explain as ordinary erosion. The oceans will carry another part of the signal: plastics, industrial chemicals, fertilizers, sewage, heavy metals, microfibers, oil residues, and combustion particles all travel through water and air toward marine basins. Deep-sea sediments accumulate slowly, which can make thin disturbances visible if they are widespread enough. Some human residues may be diluted beyond recognition, transformed chemically, or consumed by processes not yet fully understood. Still, the ocean is one of Earth's great collectors. It receives dust from continents, shells from plankton, ash from volcanoes, iridium from impacts, and pollution from human industry. If the human age becomes a recognizable layer, the deep sea may hold some of its most continuous records, not as a story of ships and coastlines, but as a fine-grained archive of altered chemistry. Future fossils may tell a distorted version of human influence. The human body itself may not dominate the record. Despite the scale of human population, humans bury, burn, scatter, protect, and disturb their dead in many different ways. And the fossilization of any individual remains rare. But the animals humans favor may be far more abundant in future deposits. Chickens, cattle, pigs, sheep, goats, dogs, cats, rats, and other species associated with human systems could appear in unusual numbers and unusual places. The domestic chicken remains a particularly strange symbol because it has been shaped so intensely by selection and produced in such vast quantities. To future paleontologists, a sudden layer rich in the bones of a fast-growing yet human-bred bird might be more revealing than a broken statue. Extinction will be one of the darker signals. If the current biodiversity crisis continues to leave a strong fossil pattern, future researchers may see a sudden loss of large animals, specialized species, reef builders, amphibians, island species, and many organisms sensitive to climate, habitat loss, pollution, and invasive competitors. They may also see the spread of generalists and human-associated species. The biological world may appear simplified and redistributed. Continents that once had distinct ecological communities may show evidence of mixing through trade, travel, agriculture, and accidental transport. This kind of biotic homogenization may be one of the more enduring signs that a single species connected the planet in a new way. The evidence remains incomplete, but the direction is visible. There is also the trace humanity leaves in the sky that later becomes a trace in stone. Carbon dioxide, methane, nitrous oxide, aerosols, and other emissions alter climate, ocean chemistry, ice, rainfall, fire regimes, and ecosystems. Those changes cascade into sediments. Coral reefs respond to heat and acidification. Glaciers retreat and leave new deposits. Rivers shift with changing rainfall and land use. Droughts alter dust. Warming seas affect marine shells and oxygen levels. Forest fires leave charcoal. What begins as invisible gas becomes, through the patient machinery of Earth, a record in mud, shells, soils, reefs, and ice. A future geologist may not know the politics of carbon, but may see the carbon. Satellites, ironically, may leave little on Earth unless they fall. Objects in orbit feel like the most futuristic part of civilization. But most low-orbit satellites eventually re-enter and burn, scattering small residues. Higher objects may remain for longer, and a few spacecraft may persist in space far beyond the lifetime of cities. Yet for Earth's geological record, satellites are likely a weak signature compared with industrial chemistry and sediment. The most ambitious human messages may travel outward, while the planet remembers the waste heat of industry more faithfully than the message. This is the final irony of the human footprint. Humanity may be easier to detect as pollution than as culture, easier to see as extinction than as philosophy, easier to recognize through chicken bones, fly ash, carbon isotopes, plastics, metals, and altered nitrogen than through any declaration of who people believe themselves to be. That does not make human culture meaningless. It makes it fragile. Meaning must be carried by minds, languages, communities, and records that survive only under narrow conditions. Geology preserves consequence. If humans become a layer, the layer may say that a species rose, burned ancient carbon, moved matter across the planet, altered life, warmed the air, changed the seas, and left behind a brief, unmistakable disturbance. It may not say what that species loved, feared, worshipped, or regretted, and this is why the question turns back on itself. If humans want to know whether an older civilization could be found, they must ask what they themselves are becoming in the record, not the first draft of history, but the last residue of it, not the voice, but the echo. The future Earth may preserve humanity not as a triumphal monument, but as a thin, damaged layer where the planet's ordinary rhythms briefly change. It is a humbling image, but also a clarifying one. Civilizations may dream in words and stone, but deep time listens most closely to chemistry, extinction, and the movement of matter. The answer that survives the evidence is simple, but it is not small. Humans are the first known civilization on Earth. Not the first life to transform the planet. Not the first species to build. Not the first animals to cooperate, migrate, engineer habitats, communicate, or reshape local environments, but the first known species to develop cities, writing, agriculture at continental scale, industry, global transport, fossil fuel combustion, electronics, nuclear technology, and the ability to alter Earth's chemistry in a way that may outlast memory itself. That answer is not a failure of imagination. It is the answer supported by the record. No confirmed pre-human industrial layer has been found. No ancient signal combines artificial chemistry, extraction, combustion, synthetic materials, global ecological disturbance, and technological residue in a way that forces science to recognize another civilization before humanity. Yet the word known remains important because the Earth is not an open book. It is a damaged archive written in a language that becomes harder to read with distance. The Silurian Hypothesis does not overturn human uniqueness in the record. It complicates confidence. It reminds us that evidence is not distributed fairly across time, that coastlines disappear, ocean crust is recycled, mountains rise and erode, sediments are buried and transformed, and artifacts lose their meaning when the arrangement that made them intelligible is destroyed. A civilization can be obvious to itself and still become nearly invisible if enough time passes and if its traces fail to enter durable geological systems. That possibility does not prove anyone came before. It simply makes the silence more sophisticated. The mainstream conclusion remains steady. Known civilization begins with humans in the recent past, after a long prehistory of tool-making, fire, symbolic behavior, migration, ecological knowledge, domestication, settlement, and social experimentation. The early cities of Mesopotamia, Egypt, the Indus world, China, Mesoamerica, the Andes, and other regions are not the sudden arrival of intelligence from nowhere. They are the visible peak of processes that had been building for thousands of years. Agriculture changes landscapes, storage changes power, writing changes memory, trade expands distance. Cities make strangers part of one system. Then industry changes the scale again, turning human society from a historical force into a geological one. The rise of civilization is not mysterious because evidence is absent. It is mysterious because the evidence shows something rare unfolding from ordinary human lives. That is very different from saying history is complete. Archaeology constantly revises its maps. New sites appear under jungles, deserts, farmland, ice, and shallow seas. Ancient DNA redraws migration and ancestry. Remote sensing reveals hidden roads, canals, fields, walls, and settlements. Submerged landscapes show that rising seas erased parts of the human story after the last ice age. Scripts remain undeciphered. Cities are found where older models expected less complexity. The evidence remains incomplete, and scholars still debate how many pathways led toward urban life. But these discoveries expand human history. They do not require a pre-human industrial species. The unknown is large enough without being forced into unsupported shapes. The Silurian hypothesis is powerful because it teaches how to keep two thoughts alive at once. The first is restraint. There is no reliable evidence that another civilization came before humans. The second is humility. The absence of evidence in deep time is not always as simple as it feels. Science must reject unsupported claims, but it must also understand the limits of its own archives. The rocks do not preserve everything. They preserve what conditions allow. They are not designed to answer human curiosity. They are the residue of processes that were indifferent to whether future minds would ask questions. So perhaps the deepest meaning of the hypothesis is not hidden in the distant past, but in the present. It asks what kind of civilization humans are becoming as seen by the planet rather than by themselves. From within, people see languages, nations, families, cities, art, grief, ambition, invention, and memory. From the perspective of future geology, humanity may appear as carbon, plastics, metals, altered nitrogen, soot, radionuclides, extinction, domesticated bones, changed rivers, disturbed sediments, and a brief warming pulse. The future may detect what humans did to Earth more easily than what humans meant to each other. That is not the answer people want from history. But it may be the answer deep time gives. Were humans the first civilization on Earth, or merely the first one visible? The responsible answer is that humans are the first and only civilization known from evidence. But the question itself remains useful because it strips away the arrogance of the present. It shows that visibility is not the same as existence, that preservation is not the same as importance, and that the planet remembers consequence more readily than intention. The silence before humanity is not a secret proof of something lost. It is a field of uncertainty bounded by geology, chemistry, erosion, and time. Most likely no industrial species rose before humans, but if one had, the search for it would not look like treasure hunting. It would look like reading a damaged climate signal, a strange sediment layer, a biological disruption, a chemical anomaly, and then asking whether nature could have done it first. And nature usually can. That is the final discipline. Volcanoes can warm the world. Asteroids can darken the sky. Oceans can lose oxygen. Fires can spread without hands. Metals can concentrate without minds. Climate can shift without engines. Life can collapse without industry. The planet is powerful enough to create mysteries that do not need civilization behind them. This makes the real human story even sharper. Humans are not remarkable because every mystery points toward hidden predecessors. Humans are remarkable because, very recently, one primate lineage crossed a threshold where its tools began to alter the planet's future archive. In the end, the Silurian Hypothesis does not replace history with fantasy. It deepens history by changing the scale. It asks people to stand between a city street and a sediment layer, between a written name and an isotope shift, between a monument and a landfill, between memory and rock. It asks whether civilization is something that conquers time or merely something time translates into another language. The known answer remains human. The larger lesson belongs to Earth. Every world that rises on its surface is temporary unless it enters the archive. Every archive is partial. Every silence has to be read carefully. And every civilization, including this one, is already becoming something the future may struggle to understand. After all the layers have been turned over, the mystery becomes quieter. It no longer needs a hidden city under a vanished sea or a machine sealed inside ancient stone. It rests in a slower image, a planet moving through time, carrying life for billions of years, preserving fragments, losing more than it keeps, and turning even the loudest ages into thin marks beneath later ground. The question of whether humans were first begins with curiosity, but it ends with perspective. The Earth is old enough to make every certainty feel young. Somewhere in the future, if there is anyone left to read the rocks, the present may not return as a story. It may not return as nations, flags, voices, songs, markets, screens, towers, or the names people gave to their own age. It may return as a narrow layer where carbon changed, where oceans warmed, where species vanished or traveled too far, where strange materials settled into mud, where the bones of animals bred by human hands gathered in unnatural abundance. The human world may be remembered less as a monument than as a disturbance, less as a declaration than as a trace. That thought is not only bleak, it is clarifying. It means that civilization is not made permanent by believing itself permanent. It survives through care, through memory, through records, through the fragile chain of one generation carrying meaning to another. Geology may preserve consequences, but only living minds preserve stories. The difference matters. A rock can remember that something happened. It cannot remember why it mattered. So the silence before humanity remains mostly silent. It does not prove a lost industrial world. It does not need to. It reminds us that the past is vast, that evidence is rare, and that even a planet covered in life can become difficult to read once enough time has passed. Humans are the first civilization the record gives us, the first known makers of cities and machines, the first known species to turn its own age into a geological question. For now, that is the answer. It is enough. And above every city, while lights burn and rivers carry silt toward the sea, the older earth continues its patient work. It breaks, buries, dissolves, preserves, forgets, and records. One day, even this age may settle into darkness beneath later stone, waiting not as a legend but as a layer,